अरे इनका वो नहीं करा
एक प्रॉब्लम है आओ
Yeah, you may begin.
Can you give us a countdown? Can you give us a count?
Okay, yeah. Three, two,
Good morning, everyone. We are team 14 and we are here to present our work on improving domain-specific QA. So the task of domain-specific question answering is about like we have a knowledge base which is like a collection of paragraphs, and given a question, we have a retriever that actually retrieves relevant top k passages from the knowledge base, and we give the most relevant paragraph to a redirect which extracts an answer span as the answer to the question. So the existing work on text retrieval actually is mostly dense, sparse, and highly representations. And on extractive question answering, so the recent methods employ like large language models and their ensembles like IES, retro readers, or new schemes. Although these methods actually achieve state of the art, they are computationally expensive, and we argue that simpler methods like the BM25 DPR can be improved further, like using some simple techniques. So we present our method, retrieve, thrice, rank, and answer. So a brief overview of the pipeline is given here. We shall look at the retriever stage. So we use an ensemble of three retrievers, sparse and dense retrievers. So sparse retrievers focuses on lexical similarity, and the dense retrievers mainly focus on complex semantic relations. So the intuition behind this approach is that smaller, simpler passages can be retrieved using exact match, and then the dense embeddings actually capture very complex abstract semantic relations. So once we obtain the top tier retrieved passages from each of these retrievers, we do weighted voting and obtain the final ranking of the top k passages. So you can see that we give a higher weightage to cold word because in our experiments we found that it improves the generalizability.
Even with the use of very large models like, for retrieval, we see that it is incapable of representing passages in a very small vector. So what we do is basically we hypothesize that if you are able to find out potentially answerable questions for each passage, we say that it actually improves the scores on our retrieval task. So basically we identify potential answer spans, generate questions for those, and use that to boost our performance on the retrieval. And so, additionally, given that our voting ensemble that we talked about is actually already powerful, we also say that we also additionally, optionally, like make use of a re-ranker module, which takes in the passage question pair and uses a more fine-grained retriever to reorder the top five passages. Yeah, so as I talked about, our voting ensemble is very powerful, and if you want to basically use like a re-ranker on top of this, we see that off-the-shelf re-rankers actually, like if you fine-tune them, we actually see that they might approach a non-trivial optimum. So we present our fine-tuning mechanism, STAF, which basically preserves the knowledge of our pre-trained model as well as prevents drift when fine-tuning. So we also did several experiments on the QA and realized that like already pre-trained models, even if they are small, perform extremely well on the question answering task, given that we retrieve the correct passage. So we leverage a small model, in our case Tiny Robota, to efficiently answer, even with while working on the efficient retrieval task. So yeah. So now, one major thing about our pipeline is that we do not use explicit question answer pairs with indices for each paragraph. So we synthetically generate the questions for each passage. We use that to basically fine tune the cross encoder theme wise. So for an incoming passage, we generate questions by identifying potential answer spans, and then we update our knowledge base and cache it. With the updated database, we query and then we fine tune our cross encoder for each theme. So, yeah. So if you look at the results, basically if you just use a vanilla BM25 for retrieval, we see that it performs nearly 70% of the time. And not the state of the art cold, but we see that it is 82%. Our voting ensemble is actually very powerful, and we achieve a 0.83 top one accuracy on that. And it is also noteworthy to note that the top five passages that we retrieve are perfect. That means, so basically, whatever re-ranking we do, it is actually same. So now, additionally, with the questions appended, we see that it boosts our performance by over 2% on the retrieval task, and also reporting our F1 score without the use of a reranker is 79%, just on official pre-trained question answering modules. Moving on with so as we talked about using off-the-shelf pre-trained cross-encoder, we see that it actually degrades the performance of our voting ensemble. So for that, we propose the S-staff fine-tuning regime for each thing. We fine-tune the cross-encoder with our novel technique to see increase in the top one retrieval score, which also correlates in our F1 score. So we see that our best retrieval score is when we use a fine-tuned cross encoder, and the F1 score that we achieve is 0.81. So now, apart from these changes to our pipeline, so we have also exported all our models into 1x per fast inference time on CPUs, and also multi-threaded them, and then exported them to fasten up the inference process. Also, so as we talked about, the voting ensemble that we have is already powerful, and if at all we want to improve our scores using a cross encoder, the problem is that the cross encoder is very heavy, so it actually uses a lot of computational time. So we propose an adaptive ranking strategy conditioned on the retrieval scores, the retrieval confidence scores of our voting, and then we see if necessary we re-rank them optionally. So now talking about our final latencies, we see that our pipeline without the anchor, that is without the cross encoder, overall we are able to, and even with the cross encoder, we are able to perform the QA task in less than 50% of the given time. Yes. So in conclusion, so we propose our R3 RA pipeline, which is a three-stage retrieval task and domain-specific question answering. So small demonstration for that. So our pipeline uses a voting ensemble, which uses sparse and dense subheadings, simple sparse and dense subheadings, along with along with automatic question answering, because manual. That's time.
No, no, no.
Okay, along with automatic labeling of questions, because hand labeling is computational. So along with our S-staff fine-tuning strategy, we achieve impressive F1 and top one scores on the task.
Okay. Let's go.
Can you go back to the retrieval section? And so, if I understand this well, you are using an off-shelf QA model, and is there any fine-tuning at least for the QA, or
Yeah, so we actually see that for our very powerful retriever, even if we fine-tune the QA, it is not improving scores by that much. It's still going to be a lot of models for each stream and not touching streams. And we also want to generalize the QA models, right? So for very small models like Tiny Roberta, it doesn't make sense to fine-tune because they're not as powerful as like huge models. So given that we also want to compute it efficiently, we choose to use the pre-trained QA models.
and let's say if you are given a thing which has words which your model, if your model requires a vocab, it does not have it. So how does your entire strategy fit into that?
So there are two ways. One, so while we generate the potential answerable questions, like the abstractness of all possible questions might be captured there. And since we are using two types of dense subheadings, we also learn the semantics of our passage, and then those passages will be retrieved accordingly.
So when you generate the paragraph embedding,
Yes.
it's still using so what's the technique we're using for the embedding?
So we use actually two things. So we pre-compute the passage embeddings. So once for DBR, once for cold one.
Okay, so for the dense one,
Yes.
can it happen that as in the paragraph now have words of which your model does not understand, and it's unable to generate the embedding, so that let's say the semantic search won't work as expected?
It might happen, which is why we actually use PM25 to augment in that particular case, where we actually look at exact words.
How is the
waiting on someone decided?
Yeah. Let me just know that. So we found out that cold bird generalizes very well because of its large nature. So we actually weighted at a greater rate, and we also gave like better rating for PM25 because of its ability to match exact like, chunks.
And just like empirically decided.
So we ran several experiments and then found out these are the best working weights
On spot.
on the training data set which you provided.
And there's the last piece. I think you are generating questions as well, right? How are you doing that?
So we just take T5 model and then so basically we take the context and the answer and we query it, like ask it to generate a question and then we generate the question from it. So for that actually we use like very powerful answer spans. We don't like take any generic answer spans. So we specifically like choose them using like better performing viewers and then basically we can say that whatever question that we get, these are like very high confidence answers for that question. Okay, what was it?
Everyone please pay attention. I just want to repeat that 6 minutes 30 seconds is the warning buzzer for you to wrap up your presentation. 7 minutes is where you have to stop your presentation. But if you take some extra time, you can, but there will be a penalty. Don't get confused. Is it clear? Are there any questions about the presentation time? Yes. The Q&A will begin at 7 minutes. And at 10 minutes, it is a hard stop. But if the judges are asking you a question, then you have to answer it. Three, two, one, begin.
Good morning, everyone. Hello, we are team 31. So, the problem statement is given our domain specific passages and the questions, how do we answer them correctly and as soon as possible? So, we have divided the problem into 4 subtasks. So, the first one is to generate synthetic data based on the given passages for a given theme. We generate question answer pairs for the given passages. And then we look for already answered questions. So if the questions already match with the already known questions, We just give the output of the already known answer and passages. And if they do not match, we pass the question onto a retriever model, which gives the passage number, and through that passage number, we find the answer to the given. So going on to synthetic data generation, we use a T5 based model in order to generate the span, which could potentially be a very answer, and we pass that span onto another T5 generator model, which generates the question for that passage, and then for the given testing data, we had generated around 4,000 questions, and the model time for generating one question was about 4 seconds.
Explaining how we answer the previously answered questions. So for that, we have used a mini LM model like architecture. Instead of the original one, which was supposed to have 12 layers, we used the one with the 6 layers, and it contains several transformer sublayers, given as a cell potential head. And for the part, this model was pre-trained on data set of 1 million sentence pairs. Each sentence pair being labeled with binary number, either 1 or 0. One in the case where the sentences are semantically same, which means that their meaning is the same, but they may use different vocabulary. Further on, we have trained our model on Quora question pair dataset, which has every data point in that dataset as a pair of questions, where the questions, when labeled as one, have different vocabularies, but they mean the same thing. Which means that there are two different questions using different words of vocabulary, but they have the same answer. So finding upon that dataset, we get a model which is fit to find out questions which have already been answered in the training dataset or the testing dataset, and their answers itself can be used to answer the new testing questions. So we found out the embeddings of the training dataset stored in theme-wise file on this, and as a new test question arrives, we find the embeddings and look for the questions in the corresponding theme. And if at all we get some questions with similarity score greater than threshold, which is also calculated in the notebook file, we directly find the paragraph and the answer from that data itself, and we return that value. And one thing extra is that in the testing part itself, if at all we encounter some question which has already been answered previously in the testing part, so those questions also get added up in that basically dictionary or the file where we have the embeddings of the training data. So every time there's a question which has its answer of some other question, so that can be directly found and that is very fast and efficient. Because finding for a pair of questions, finding the similarity and if at all they have the same answer, it can be done within 11.5 milliseconds. So that is really that really helps us get the inference time down quite significantly. Also, the disk space in the model and the file that I was talking about is not that high. 80 MBs of is the size of the model on the disk, and 5 MBs is the size of the file which contains the embeddings, as well as we can augment it for the disk data. That was about the previous time.
So Asha's now is given a question of something, we need to find a paragraph of the particular thing which can answer the question. We have experimented on recent state-of-the-art models. We have tried DPR, next class retrieval, multiplied digital byte form, multiplied digital byte form, etc. But we had a trade-off between accuracy and inference time. And DPR implementation was taking high inference time than multiplied digital byte form v1. But multiplied digital byte form v1 with less accuracy, it was taking less inference time of 0.115 seconds. So we preferred multiplied digital byte cost v1 over DPR. And we have multiplied digital byte cost v1 for our passive retrieval.
So after finding the paragraph that has the answer to the question, the final task that we are left with is to find the span of the answer to the question from the retrieved paragraph. For this, we have used several pre-trained models like Dynamic Tinybird, Roberta, Colbert, and Albert. Initially, we were supposed to complete the task in 0.2 seconds, and so we proceeded with the Dynamic Tinybird model, which has the best inference time among the all, despite having a lower accuracy. After increasing the time limit to 1 second, we changed our model to Roberta, as it provided us a great improvement accuracy over the Dynamic Tinybird model. We preferred Roberta over Colbert and Albert to see the passage retrieval task as well, like to answer the time that is required to answer the passage. We considered that as well into account. Now we tried training these models on the 300 themes that were provided to us but we found that the models overfit the data and there is no improvement in the validation data set. So we preferred not to train the data on those 300 themes to reduce the computation costs. As you can see, the average inference time per question for the Roberta model comes out to be 0.5 seconds. So this is our final pipeline of the whole model, and the average runtime per question comes out to be 0.3 seconds. Thank you for listening to us, and now we are open to questions.
So, in the given pipeline, we are only doing semantic search. That we are just doing the semantic search.
In what part are we asking?
In the retrieval, in the passage retrieval.
The passage
Okay, how we are doing that?
in passage retrieval, right now, I'm laying the deep and implementation, right? It's a bi-encoder model, two different encoders for passages and questions. So you train the model on the training data we have, and we store the embeddings for it. When you use a new query, we calculate the embeddings for the already learned model, and then we match it to the similarity also. So give the top one passage. Currently, we're taking only top one passage.
So, okay, so you are not doing any sort of revamping, and also there is no syntactic similarity sort of search.
It's more of a generative. Yeah, we are doing synthetic data generation, but as a facilitator mode is not a generative model here. But yeah, we are using synthetic data generation.
In the answer prediction, you are
Yeah.
and in the so the paragraph embedding generation again. I'm not sure if I did that, but do we have any fine tuning or?
Yeah, we did fine.
How to do that?
Like, we actually used to passage retrieval implementation. In DPR, it was like a big model. So the pre-trained DPR implementation is like smoothened over all tasks because you don't know what task you use the pre-trained model. So we fine-tuned it on the 300 distribution themes which required for it. But in the case of multi-queue distributed cost even, it was not like smoothened completely. So even fine-tuning didn't give us much difference in response. So we fine-tuning was just a computation cost. So that's why multi-queue distributed cost even. We just use the pre-trained model.
So I was asking if you were fine-tuning for that. So this is like
generalized, not for particular.
So what you do is try fine-tuning for that.
Yeah, we did try that, but the thing is like in case of big models, it's like fine-tuning a particular theme was not much effective. Like, we are given like some 100 data points to drag it from a smoothened model to a particular fine-tuned task, which was not sufficient. So then we took a collective of all these, had decent number of questions which are like pulling the model to a particular task. Then just have fine-tuning for a single.
So I mean, your total model size was around 80 MB. What your total model size was?
Yeah, the binding is for like previous answer questions that was around 80 90 MB.
And there's a so you are generating some questions and you are also looking at those older generated data, right? So can you tell me basics around what better you would achieve with the generated data?
So in terms of inference time, like found out like 0.8, like 30% of all the new questions were repeated even in the given test data.
Yeah, not in the test, as in while you were just building models and everything. So when you were able to find that your generated data set had questions which like you were inferring for.
Yeah, so that is what I'm telling. 30% of the data that we get generated was repeating while we are in, answering the new questions. That's what
You're saying that you generated the data and you found that the same question was present
at the test data. Yeah.
Do you have any metrics on how much improvement you saw after using generated data and without using generated data?
Thanks.
Team 90. Ready? Are you ready? 3, 2, 1, begin.
Hello, good morning everyone. We are team scientists and we are here to present a solution for the DevRev problem statement of question answering and answerability check. So in this case, we had to face three questions. The first one was to map each question to a given paragraph as there were multiple paragraphs for a given theme. The second one was to check if the question is answerable by any of the given paragraphs. And the third one is to actually answer the given question. So this was the initial model that we were planning to use. This is the bias model, and it has pretty good F1 score according to research. But upon further researching, we found another Stanford research paper that said that by replacing the initial few layers of BiLab with BERT and creating a hybrid BERT plus BiLab model, we can achieve even greater F1 scores. And the researchers at Stanford were able to achieve an F1 score of around 85 with this method.
So we begin with the data pre-processing, in which, as Miraj said, that we were given two CSV files, one containing questions and one containing paragraphs with their themes. So with Denison, we first did the similarity checking between the questions and paragraph and try to append all the questions having same uh, meaning as the question given. Every paragraph having the same meaning as question given to that question. For that, we first match for a specific theme. First match all the questions with all the paragraphs, and the paragraph having the maximum similarity score were appended back to the question. In this way, we are having a CSV file with a specific theme, questions, and the paragraph related to that question, so that we can answer that question from that paragraph.
So after that, we get a question and context pair for each and every question for our data set. We pass that question context pair to word preprocessor and we get three outputs. First is the word token, second is the mask, and third is the token IDs. This is the X data of our training pipeline, and the basic sequence of this is that the first is the CLS token, then the context tokens, and then padding with separator. This length is 461 index, and the separator is at the 461st index, and then it is followed by question token, then separator, and then padding. For just the training pipeline, we needed to do another pre-processing that was for the Y dataset, and we needed the token start and token end index to train our model. But in the spot B2, we were given character start and character end index, so we had to do a bit of pre-processing there and get the final Y data with the token start and token end index. Then we pass the X data to BERT. Here we use BERT base and case, and it gives three kinds of features. First is token encodings, second is pooled encodings, and the third is sequence features. But to build anything upon BERT, we need the raw data of the sequence features. So that is what we use: question features and context features.
So after that, both of the now that we have the features for the question and the context, it is being passed to the attention flow layer according to the model. And this attention flow layer gives us two attentions, query to context and context to query. One of them, the former is being softmax, while the latter is not. Both of them are being then passed on the bidirectional LSTM, which gives it directional as well as positional context into their token embedding. And then from there, what we do is that now that we have this contextualized embedding of the context, we use two dense layers. One is for LSTM plus softmax to find out the logics for the end index, and another dense plus softmax layer to find out the logics for the start index. Now that we have this data, then we use it for evaluation and training, and that's how the entire pipeline is.
So before that, after the entire model was built upon it, we thought that to fine tune the entire model, we needed some synthetic data to modify upon and work upon it. So first, what we did was it was a basic idea of like producing paragraphs that have an absolute answer. Like we remove the answer of the training data paragraph that were already present and replace them with some null strings, and that presented us with a set of paragraphs that have no answer or absolute or false answer. So we appended the net amount of data with the original dataset and used for fine tuning. And the second step was a basic back translation step in which we basically converted the questions in back translation into a different mode of language and then reconverted it back. That preserves the integrity and the context of the question, but the model in which the question is asked to the user in answering is different. So basically, we have a larger set of questions for a particular paragraph to answer for, and that provides us a greater clarity in answering questions.
So now we come to the final analytics and analysis. The training reference score that we were able to achieve after just 12 epochs was 64.3 and the validation was 48.6. We didn't have enough time to train our model for a greater number of epochs as the computation was very large. But even after 48.6 validation score, as you can see in these examples, like which current iPod features the largest data search capacity, the answer it was expecting was iPod Touch. Our model predicted 128 GB for iPod Touch, which is, I would say, more descriptive, but as the start and end token index are different, the F1 score is going to reduce. All these examples actually reduce the F1 score, like iTunes software. The Windows part was skipped until Microsoft was predicted. And these kinds of examples actually on manual analysis it is correct, but they decrease our F1 score. And finally comes to the answerability question. So in our test data set split, there were 4987 questions that were unanswerable, and in the data pre-processing stage, we set the start and end index of unanswerable questions as 0, and our model to successfully predict 3666 questions out of them. So just for the answerability part, the accuracy of our models comes to be around 73.51, and that is all from us. And now we are open to questions.
For the QA, it looks like you are doing a lot of things. So, can you, so first thing, did you use some off-shelf to just try it out and see if you are able to implement that? So, I think you we are getting our validation about 8 point.
Yes.
By the end.
So the reason for that is that first of all we used BERT base because BERT large was giving so many training parameters, and secondly, the researcher that we followed, they actually kept the BERT trainable for the first few epochs. So that actually the with the computation power we had, that was showing 44 hours for one epoch, that was not doable. So we set the BERT non-trainable and base from the starting. So that is the reason we are getting this accuracy, and on top of that, we only trained it for 12 epochs and fine-tuned it for 3 to 4 more epochs.
You would have figured out this data set is from squad or
yes, squad video.
So did you, as in, so there are models that are
yes, yeah, we tried Roberta, Distilbert, and many other, but all of them were not able to give definite answer for answerability. And on top of that, this model is trained for larger number of epochs and with more computation. It actually performs way better than a tiny robot and everything. So that is why just to show the model architecture, we went with this approach.
So for the task one, what was the reference score?
Task one, the matching. Yes, sir. Actually, in matching, there are many instances
instances where our model is able to predict the paragraph that has the answer, but not the paragraph that was expected. Like for a several thing, there are many paragraphs for a certain thing, and there are many different paragraph that contains the answer. So we did not actually calculate the F1 score for task one. We calculated the F1 score at the end because the paragraphs were pretty ambiguous. Like so many paragraphs contain the answer.
And yeah, can you just remind the retrieval step for us? How you are predicting the paragraph?
Yes. Genesis.
So for paragraph retrieval, we are using Genesis, which is a pre-trained model for semantic sentence matching, and we just give question and match it with a list of all the paragraphs related to that thing, and the paragraph which are having the most similarity matching score, like the cosine similarity, it matches. So which the paragraph having the maximum score is appended back to the question. In this way, we are getting a new CSV having a theme for that question and the paragraph.
The similarity is between what?
The similarity between the semantic of both questions and the
And when we say semantics, how are we generating the semantics?
Genesis thus vectorize all the questions and the paragraphs also. And
What does Jensen mean?
Jensen is a pre-trained model, sir. So it is cosine similarity for matching the vectorized questions and the paragraphs.
So it kind of matches themes and words from questions to paragraphs, and the maximum matching is expected to contain the answer.
And do you have any, I'm not sure if you have already answered questions, you are doing that, right? So if you already have answered questions, we are looking at those questions as well.
Yeah, we already answered. We don't check for that because we didn't make a model for theme specific purpose. We generalized it for any complexity base. So we are not checking the already answer because then we had to use cache and all. We didn't use any of that. We were trying to make it generalized so we can give it any paragraph and question and it can give us the answer.
How do you handle for passages, for paragraphs, where where some of the words are not present in the grammar of the existing model?
Like like for every passage and the question, it gives a score like 0.5 and so if the paragraph and questions are maximum matching, then it gives a score of about 0.7, 0.6. But if the paragraph is having some of the words similar, but the semantic is not matching, then it gives a score of 0.2 and 3. So from that we can say that the paragraph is there, it's matching, but the answer is not available in the paragraph. It's like that.
For if the words are not in the dictionary, actually what the model does is that it kind of breaks the word into subwords, and those subwords are predefined, kind of the similar way like word uses. So that is how some.
So at runtime, do you compare for each question which is the closest paragraph using
Yes,
this?
Yes.
So you feed each paragraph to compare to the model, and it gives you the semantic.
Yeah, with the same.
so basically, we tried this with Word also. Like Word implementing all the questions and paragraphs with Word, but it was taking a lot of time. And Jensen just did it in 10 minutes. So it was like that.
And it is specifically trained for this kind of similarity.
It is-
my about is a generalized model, so it was not giving the same results.
Do you have metrics around how much time did it take to compute?
Yeah, the final.
One question paragraph.
Oh, for similarity matching.
Yes, for semantic.
For similarity matching, we have not calculated, but the overall time was about 10 to 15 minutes. It matched all the paragraphs with the questions.
And the overall runtime for our test data set that we were provided at the last test, for the whole data set, it took around 33 seconds. For the whole data set, 3,000 or 4,000 questions were there. It took around 33 seconds.
So you basically feed all the paragraph and all the questions.
Yes, both
And
yes.
it gives you for this
For a
question,
specific thing, we are pretty.
right, for the specific, and then it returns you that this is the paragraph that answers this
And
question.
this is the suitable answer.
And you were able to do the entire task in 23 seconds.
Yeah, the final CSV that we were given, the entire testing was done in 33 seconds.
Was it an over optimization with it or?
No, actually it was from a premium GPU from Collabora Plus. So the computation was pretty good. That's also a factor.
Thank you.
Thank you.
Good morning, everyone. So this is our approach for the DevRev problem statement. So basically, our pipeline consists of three parts: the retriever module, the rewriter module, and the reader module. So let's start with the retriever module. The basic task of the retriever module is to generate embeddings. So initially, we tried models like Word2Vec and FastTech. These models are really fast. However, the quality of the embeddings that they generate are not that great, in the sense that they're not able to capture the semantic information between the context and the queries. So we resorted to transformers in there, and we used Google Universal sentence embeddings, and we found that the quality of embedding that is generating is able to perform well in the downstream tasks that we have. The similarity that we have, similarity metric that we use is cosine similarity. We also tried the Euclidean distance between the embeddings. However, we found that cosine similarity performs better. And cosine similarity is basically just the dot product between two normalized vectors. Right? And then as I said, we use the embeddings from the transform model. However, we found that there is a chance to improve the quality of the embedding that is generating. So we tried two more methods to improve the quality of those embeddings. And those two methods are contrastive learning and adaptive margin regularization. Basically, what contrastive learning does is it takes a query and a similar context, and its goal is to make them closer to each other in the latent space, while making the dissimilar ones further away from each other at the same time. Now, what adaptive margin regularizer does is it performs whatever I mentioned earlier, as well as it creates these class-wise boundaries, and the margin of these boundaries is dependent on the number of samples we have in that class in the training set. So that in that way it performs better in the classification selecting paragraphs later. Moving ahead, we calculate the similarity between the context and the queries, and then we have a sorted list. Out of that sorted list, we pick the 15 contexts with the highest similarities, and then we pass it on to the re-ranker model. The goal of the re-ranker model is like initially we compute embeddings, but they are computed independently. The query and the context embeddings are computed independently. However, the re-ranker model takes into account the context and the query at the same time, and gives us a new probability score that what is the probability that this particular query is answerable with this context, and then it rewrites it. And from this, we choose, for example, we choose two of the most, we choose two contexts with the highest probability, and then we pass it on to the reader module. The goal of the reader module is just to predict a span and another probability score. The span is basically the answer, and the probability score for the two models, and we select the one which has the highest probability score, and that becomes the answer for all five.
So now I'm going to explain about the optimization that we did to make our instance time faster. The first was the choice of language model we used. We used lightweight models such as Tiny Bird and Robota Tiny for the ranker and the reader models respectively. Using these lightweight models instead of like word based or something like that gave us a score improvement of 0.2. The second was pre-computing the context embeddings. So basically, we pre-computed all the context embeddings and stored them in a vector database. So that during instance time, the similarity matching is faster. The third and the biggest optimization that we did was parallelizing on the CPU. So basically, we used a library called Ray, which is a data parallelizing library, which creates n instances of your model and then parallelizes them on the n cores, and thereby reducing your instance time by a factor of n and being 2 in the Google Colab period. Okay, so we also tried various experiments, some of them which we were not able to include due to the resource constraints. The first and the biggest one was generative pseudo labeling. So basically, what this does is create questions given a context. It creates like pseudo like it generates questions for the given context. This uses the transformer architecture, and we saw that on CPU it took 9 minutes to generate one question. So this was totally out of question to do. Next thing we tried was data augmentation. Basically, as we explained earlier, AMD REG largely benefits on the number of training samples you have from each class. So we use data augmentation to synthetically increase the dataset size. We saw a drastic improvement from 0.5 to 0.7 using data augmentation and AMD REG. Next was using two specific models. We found out that fine-tuning the question answering modules on specific themes basically overfit the training data and gave us a pretty bad score. So we did not continue with that. There's the final pipeline. We can see that the pre-computed embeddings and a single query is passed onto the retrieval module. The top 15 passages are selected from the similarity score. If the similarity is less than a certain threshold that we set by doing a hyperparameter search, if it is less than that, then we directly say the answer is not possible. Otherwise, it goes into the reader and the reader module. Okay, the final result is that our pipeline achieved a score of 0.74 on your metric, so that the one that penalizes the extra latency time. We got a score of 0.74 for the retrieval task and 0.71 for the question answering task, and this was all done on the CPU. We believe that more work can be done in this field. Basically, we could do things like average query expansion. We could not do this because of the time crunch we had. So basically, what average query extraction is that it takes the top k retrieved passages from the given query and averages averages top k context embeddings, and then uses this averaged vector as a query again to re-retrieve the passages. Basically, the intuition behind this is that uh, like it uses the semantic information inside the context embeddings to retrieve better passages. The second thing you could do is to increase the training data set size. So basically, the AMD Red benefits from the large training data set, as we saw in the experiment earlier, and like that's
Do you always take the first 50 best passages and then do the
right. So we chose the top K for both the retrieval and the re-ranker. We did a small hyperparameter search, so 15 and 2 were the Ks that we used for each step.
Yeah, I mean, there's like an embedding search for the message retrieval. It's only the embedding search.
Embedding
As in the, so you're generating the embedding for the answer.
yes, sorry.
So you mentioned that you are using the USE, the universal system. What are the downstream tasks you evaluated them on? I think how did you figure out that for this?
So basically, what we did was we set the re-ranker and the reader modules. We fixed them and then changed the retrieval modules respectively. So we used word to vec, doc to vec, and the transformer models, and then evaluated directly on the that was given to us the final evaluation. And Google Sentence Encoder did the best. So even though it had a little more of a inference time of creating embedding, it took a little more time, but the quality of embeddings was the best which we found by doing experimentation.
Every time we evaluate, we always evaluate on the competition metric. So even it might be possible that a single model might take more time, but eventually the metric is calculated by incorporating the time it takes. So we only look at the final metric.
What's the latency you were getting
Around 0.5 seconds, so 500 milliseconds
for the entire?
for the entire.
Just for the retrieval step? 0.2 or 0.02 seconds. For given a set of 15 minutes.
Which vector did you use? You mentioned that you were using that.
Yes. So I think we use Facebook as face.
Right.
So I used to you have metrics around comparison of USC embedding and Robota that you mentioned.
Robota and USD, right? So what were the differences? Right, we do have. Right, yeah. So we have the sentence word and Google sentence encoding the accuracies are good. And these are the reported accuracies. So basically, whether or not the top K have top one have the answer. So these are the top one accuracy.
And how do you decide the answerability of a question?
So that was given in the test training data set that this question is answered by this passage, right? So if the question and answer similarity, question and context similarity is high, the top one, the first passage which is selected, if it is the actual answer to the question.
And this universal system code, like I believe there are architectures of this model. So which architecture did you use?
We used the one on the TensorFlow hub. We're not really sure. It was a Google Center encoder we found.
Yeah, last few. Are you guys
We mentioned that we tried doing it, but then it did not work out.
Okay, when they did not work out, I think it was indicating that
It was all fixed.
and anything, I guess you did try the question generation, but
It was taking too much time on the CPU. So like 9 minutes per question.
what was your technique like? Which was taking
It
time?
was a generator model.
Basically, a large language model, something like the backbone of God. So when like you pass in a context and you try to generate a question and an answer with it. So when you take a transform model, it was give you like you don't have the back and forth to perform it. It was taking maybe 9 minutes to generate a question. So now you use the model using it in the Python.
And you didn't try any of that sort, like figuring out mentally recognize recognition and just
Everyone, these stickers are for you when you're going after your presentation. Please collect them. Karthik? Ready? 3, 2, 1, begin.
So a very good morning, everyone. This is a solution for the DevRev problem statement. In this solution, we have tried to improve domain-specific question answering using existing pre-trained language models and managing the training and testing data robustly. So before I tell you about the entire solution, we just want to
Ready?
Yes.
3, 2, 1, begin.
A very good morning to everyone present here. This is our solution for the DevRev problem statement. In this solution, we have tried to improve domain-specific question answering by using the existing pre-trained language models and managing the training and testing data robustly. So before I tell you in detail about the entire solution, I would like to show you an overview of the solution using this flowchart over here. So as you can see at the start, we have our input, which is a question, and a set of paragraphs that may contain an answer to that question. What we do is we pass them through a deep passage retriever, which basically outputs the top k passages which are most probable of having an answer to that particular question. Now, after having experimented with a lot of different k values, we found out that k equal to 5 gives us the best results. What we do is we basically concatenate all of those passages and we kind of map their start indexes and end indexes in a different container. Now, this corpus of 5 passages and a question is passed on to a feed-forward neural network, which basically predicts if answering that particular question using that corpus is possible or not. If it is not possible, we return -1 and we end our program. Else, we basically move on to our solution for the second subpart of the problem, where we basically find the answer, the start index of the answer in that passage in the corpus. So, for the second part, our base model is a Distilbert pre-trained model. We have fine-tuned it on the SWOT V1 dataset because in the first stage itself, we reject all the questions which do not have an answer. So we fine-tune it on the SWOT V1 dataset. Now this fine-tuned model is again fine-tuned on 21 clusters that we have created out of all the things that are present in the SWOT dataset. Now why this extra fine-tuning? Because after going through the existing literature on the applications of BERT models in domain-based tasks, we have realized that gradual downstreaming on generic BERT models improves their performance on any given domain-based task, be it question answering or anything else. Then we again fine-tune it on each theme, on all the points in that theme which are present, as well as the points that we have synthetically generated. And we cap them to a value of 10,000. Then we have our final model, which outputs the index, the starting index of the answer in the corpus of the 5 passages, from where we calculate the original paragraph ID and the starting index using the mapping that we had done earlier. And we also rate the text answer. Now I would like to call upon my teammates to elaborate on the solution.
Okay, so in the first subtask, that is the where we are using a deep passage retriever to find out the top key passages which we have experimentally found out to be 5. In this case, we have tried with 5, 10, and 15. So we have found out 5 to be the best case. We are using the deep passage retrieval network by Facebook research, where we take the sentence and the context that is a paragraphs that is presented in the test data, and to complete this yes and no model, that to answer the question of answer plausibility, that if the answer is present in this key passages or not, we take the question and the context pair and pass them to an SBERT encoder, where the SBERT encoder takes them as sentence transformers, take it and with the context pairs as well as the question pair, and finally push it through a feed-forward neural network to finally give give it a possibility score of the answer being present inside the top K passages or not, to finally produce further downstream.
So, okay, so now that we have the results of final results of the yes and no model, so we only take those data points which the model tags, the yes no model tags to tags yes. So what do you do is the we take a
we take the pre-trained model, pre-trained bird. We take a pre-trained digital bird model from Hugging Face. We fine-tune it on the whole of squad dataset, and we store it back on Hugging Face Hub. Now, the squad dataset contains approximately 650 themes, varying across various domains. What it is, we took SBOT model, we put in the themes, and what you get is a 384 dimension deep dense 384 dimension dense vector which preserves the meaning and the semantics of the theme. So by using a k-means clustering algorithm, we clustered it into 21 themes, 21 because this was the best value we found using the ALGO method. So now for each cluster, we have taken 10,000 themes, 10,000 data points, that is 10,000 question and answer pairs. This includes some synthetic data points which we have augmented from the original data using the NLP org library. We also have some of our own methods to augment this data. So finally, we fed in this 10,000 data points into the already squad fine-tuned model. And for each of the 21 clusters, we get a clustered fine-tuned model. Now coming to the training part, we are given 14 themes, I think, yeah, 14 themes for which the questions and answers were there. So for each of the 14 themes, we took the nearest cluster to it, of course, by using the cosine distance, the lowest cosine distance from that. And we again generated, like, we again capped the number of data points to 300 by including synthetic data here also, using the same methods that we have used while creating the clusters. So now these 300 data points were fed to the cluster which is nearest to it, and we again get a theme-wise fine-tuned model. Now coming to the testing part, we were given questions for approximately 30 themes. So we fed it to a function which checks whether the scheme was present during the training phase. If it was present, we directly fetch the model that we have already trained it. Else, we find the nearest cluster to it, the nearest cluster, the model associated to it. We put in the questions to that model, and we get the final output. So the final output will basically contain the starting index of the answer. So we already had a map which kind of maps the starting index of the top of the key sentences to the original corpus. So from there we can retrieve the original paragraph ID, and we of course have the answer index.
So now comes the training testing part. So now comes the testing part. So here, if we find a direct match between the theme of training set and testing set, so we directly use the model which was trained on that particular theme from the training base. Otherwise, we find the best approximate cluster using centroid distance, and we use it on top of our baseline model. So this is our final solution to the problem. As you can see, it is captured nicely in this flow chart. We can come up with better values for the hyperparameters involved if we are given access to better accelerators. Currently, everything is done on the CPU, and also if we are given, if the constraints are loosened a bit. So that's it. We are open for questions.
Can you move back to your targeting? Try to zoom in a bit.
Yeah. Ushan, zoom. Back. Which part?
So when you say A to the 5, then a 15 is the hyperparameter. So did you also try to tune it via better threshold marketing so that I take this paragraph only if the threshold is greater than this and try to hyperline and then take that threshold as a hyperparameter and use that instead of using KB? Did you try that?
So in this context, we did not use any generated pairs to find out the threshold. So we only tried out empirically find out the different values of threshold. We did not try that.
Okay. So essentially, you are figuring out first a paragraph with a vector matching to it. How you do that vector?
For that, we're using passive retrieval model. So what we're using the sentence and the context pair. So this sentence is being embedded using SBER. As we know, what is the more to the word attention, the sentence attention of the word override, because we need the entire sentences to feed into the next layers. And since we're using self-attention, it is also important that with the sentence retrieval, the context gets saved in each of the attention layers. So when we are performing this task, in the dense vector that is being created instead of TF5, TF4, BM25, which are the sparse processes, we're using a dense process because we are trying to contextualize all the possible paragraph that is there with respect to the similar question. So the matching is kind of unique.
Yeah. How do you do the matching? So you have a qualitative and you have 100 vectors in the paragraph set. How do you match?
So we match it in this way. So for each of we use a dot product similarity to maximize on that. So firstly with the S-word embedding as well as the question embedding. So we take each question and from all of the top 5 questions, we rank them. We use it means we give a positive metric to it, and all the others give them a negative metric.
Okay, so you guys when you so you mentioned that you are doing criteria based on theme testing stuff. Did that help?
Yes, sir. That did boost up the F1 metrics. I think we have a slide where we have tested on the squad V1, squad V2 dataset, and these are kind of the metrics. This is everything included, and this was a baseline Distelbert model, which was fine-tuned on squad V1. So,
Move the table a bit. Yes.
Yeah, can you guys explain that?
yeah. So we have tested it. This is the first model, like we have implemented whatever we have said, and this was the baseline model that was only with squad V1. So as you can see, there is a significant improvement of F1 scores. There are some anomalies, but overall, it's an kind of improvement.
What's exact?
What's exact?
So in the C column,
Yeah, this is an exact match, whether the question exactly matches the one answer that's given in the squad V1 data set.
Use the exact score type decreasing by a lot.
Is because every time it gets the sometimes the exact answers like we've seen sometimes it's apple but the answer is given as apple computer. So in those cases if there is no exact answer just reject it.
Okay. But the medium use is still the same thing. So you are not doing any question generation.
Yeah, no, we are not specifically generating questions, but we are kind of tweaking the whole passage. So we are using this library called NLP POP. So we kind of have 3 or 4 different methods of like generating different passages from the passage given. It's kind of like here using word to vec or transforming each word, or and another thing is word net for taking the synonyms of each word. Might be sometimes we are kind of replacing a word with an antonyms. So what it actually did is our main mechanism was like if suppose from I to J in a particular paragraph lies our answer. So we just take up the word, we take up the passage from 0 to I minus 1 and from J plus 1 to the rest. And we pick up all the sentences from there. We kind of rearrange it. So this is our basic part. And on top of it, we have 3 or 4 functions. One is one kind of replaces a word with synonyms, another with antonyms, synonyms from 2 different word to vec and word net. So we are using a combination of this. We're kind of using a random number generator. So it kind of randomizes the whole process, and like we are augmenting the paragraph that way. We are not generating any kind of extra questions because that will take more time.
And in the pipeline, were you using already answered questions or not?
Yeah, we are using kind of already answered questions. Basically, we during the testing phase, yeah, yeah. So during the testing phase, like a lot of the questions and the paragraphs were seen. So we are kind of taking out the unique questions and paragraphs, and like in the testing phase we are doing. It's kind of like we are taking out the unique paragraphs and finding.
How do you figure out if that question has already been answered before?
We're just simply checking the question, like it's like we're putting into a set. We are not kind of using the models to.
So that's like a covering transaction.
Yeah.
Hello everyone, I'm here in Fortnite and I'll be presenting our solution for the problem statement. Yeah. So before I go dive into the detailed solution, let's just give a brief overview on like how our solution is structured. So the first part is we have a ranking algorithm. It's basically given a set of paragraphs and a particular question. I'm gonna based on this question, I'm gonna reorder the paragraphs in order that like the first paragraph is gonna have most of will have the answer and so on and so forth. And then the second is a neural network, which will basically decide if a particular paragraph question can be answered or not. And if it can be answered, then I'll have a last part, which is again another neural network, which will basically extract the span of that answer in the paragraph. Yeah. So this is how our overall pipeline looks. Given a question and a paragraph set, I will have a ranking algorithm which will rank those paragraphs in an order. And I will take, let's say, top 10 or top 20. And I will concatenate the question and the corresponding paragraph. And I will have a classification module, which is basically classify, the binary classify that it can be answered or not. If it's not, then I will go to the next paragraph, do the same thing again, and I will just reiterate it again and again till I find one paragraph in the top K. And once I find one, I'm gonna have an answer extraction module, which will basically extract a particular span from the paragraph. And yeah, and if none of the paragraphs are the paragraphs true, then I will just minus one, saying that's no match. Yeah. So coming to the ranking, the first preliminary thing which we did was a simple word to word of the questions and the paragraphs, and just find gain and reason. But this actually did not work as we expected. The main reason being, since for a particular team, we have like a lot of paragraphs, and what happened is that all of these paragraphs end up with a similar word to word embedding because they already have the same kind of keywords. So what we tried was this BM25 algorithm. It's basically like K5S, but it's like has this dagger course approach. So let's say if I want to know who is beyond sun is, then a paragraph which has the words, which has the keyword sun written more number of times rather than a generic Beyonce paragraph, has most likely gonna answer the question. And we fix with BM25, right? Yeah. Now coming to the data generation part. So we noted that there are certain themes in the given data set which have like high imbalance between one and. So what we did was we basically generated false fixes for particular theme by just removing the particular answer extracts from the paragraph, and we basically like appended back into the overall data set, which increased the size by 20. And then coming to the task 2, what we did was, since this is an extracted QA task, we can jumble the particular sentences in an order. If we can maintain the indices corresponding, then we can create new data, new sentences, new question paragraph pairs for task 2. We also considered paraphrasing, but we kind of like resisted due to the time constraints. It took on approx 1.5 minutes per paragraph. Yeah. Next, now coming to the first module, classification. We used a simple pre-trained language model plus a single layer MLP head to clarify whether a question paragraph can be answered or not. Yeah. We tried like 5 different state-of-the-art models. The first one is Bert, Albert, Roberta, Distributed, and Miela. And Albert had the new number of parameters, whereas Roberta gave the best test accuracy. So that's a trade of between test accuracy and parameters, and we can like enter with Miela, which had almost a similar test accuracy, but like much less parameters than Roberta. Okay. Now for the extraction model, it's very simple like the classification. Instead of a binary classification problem, it's just a simple regression problem. I will have a single MLP layer to predict the start and end instances of the question of the answer in the paragraph. Yeah. Now coming to fine tuning. So on the day, so we are just given questions and paragraphs. And what we are trying to do is like creating false examples for the task 1. Very similarly, by just mismatching questions and paragraphs. So I'll just take one question and a paragraph from another time, I'll just match them up. That's a false example. And for the second task, so for the second task, we did a simple substring matching. So given the answer, I'm going to try to find a particular answer in the paragraph. And if there's only one instance of that answer, then I can just get those indices, and that will be like my data for task 2. And if there's like more than one instance of that particular answer in the paragraph, then I'll just discard it. Yeah, next. Okay, so that's just a trade-off between should we go with like one generated model or a specific model. And what we ended up is, so what we decided was to go with like one general theme independent model to answer all the themes. And there are like four reasons. The first reason is human intuitive. So we don't actually have a domain specific knowledge in this data set. Let's say if one of the things was based on biomedical imaging or biomedical questions, then I would need a separate model to answer that. Since in this case, the general things are like almost like well related to them. So we can just go with like one thing independent model. Yeah, next. And the second one is that there are certain things which have like very few training examples in there. So if I'm gonna have a model for those teams, then it's gonna be like highly overfit them, and it may not like perform well when I give like an test data out of it. Yeah. And the other two reasons are algorithmic. So we did a basic HTTP scan algorithm, HTTP scan hierarchical grouping to find if there's like actually like grouping in between the teams. So what we did was we concatenated with all the paragraphs of the same team and just ran this hierarchical clustering algorithm to see if it like actually has like more clusters in it, and it only returned two clusters. And then the final one is simple TLC projection onto two dimensions, and we can then like visualize them on uh, modular companies, and it give like 30 separate, like properly separate like teams. So there was like no like actual incentive to like group them to have like specific team specific models. And so these are some different sensors which we got, and the top three classes which had the highest line, the top three classes which had like ran at the farthest. Yeah. And so this is our runtime analysis. The whole pipeline takes around 11 hours to run. So from the start of training, data generation, till the prediction of the data. Yeah. Yeah. Thank you. And any more questions? Yeah. So let's say if I have a clean paragraph, and if the first paragraph has the answer, I'm done. I answer back about that. And but let's say if the first paragraph doesn't have the answer, then it will take like longer for it to like, find the answer. So then, so we have the classification module, which basically like actually says if the particular question can answer or not. So the classification module is medium backward plus a one layer MLP set, which basically classify as like one or zero.
So we use the algorithm DM25 to actually get the top 10 paragraphs that have the similarity to the question. And then we run this classification module on these paragraphs.
So these are like the highest one. So these actually took the so maybe it's because of BM25 is like BM25 is not like performing best with like materialism like beyond human error index. So maybe these classes are like hard for BM25 to like score them. Maybe that would be a reason.
Did you guys try just taking the first answer, which is the PhD by your Did you guys try just taking the first paragraph that is given by your
Yeah, so that's how we proceed. So
you are taking top the paragraph from
yeah.
the and then we will
Yeah.
We have matrix that suggests what the fourth part is the first paragraph.
Oh no, we don't do rewriting. So we just take scores from the original answer.
You are saying rewriting.
No, it's like we take the score from BM25 and then we just take the classification head and move through the from the highest scored paragraph to the lowest in that top 10. And then as soon as we reach a match, like as soon as the classification head says that yeah, this paragraph answers the question, we move to the next module.
So do we have a matrix that suggests what's the accuracy we're getting with different value of k? For example, like k equal to 1, we just take the
yeah. So go to that. So we kind of like wanted like 90% accuracy for the retrieval. So for go to that, which gave which like saturated around 50, take 50, give like 90% accuracy. For VM, we got like around 20.
Can you go to this?
So let's say if I have a answer particular sentence, I'm going to take the start index of the sentence. I'm just going to jumble the say all the sentences in that. sentences, I have like 10 sentences in a paragraph. And let's say the third sentence actually has the particular answer. I'm just going to jumble the whole thing, but I make sure the order of the indices are like jumbled in such a way that I can just send it again. The new answer.
But don't you think that in creative document, here your hypothesis is that an answer is in a sentence, right?
Yeah.
Which might not be the case.
So we are doing this for only those paragraphs that in the trained data set that already answer, that we have the information that they answer the given question.
We already have the answer extract from. We just going to jumble them to create like more examples. Like examples which are like jumbled sense so that model.
And you are saying that
this is extract case.
is that okay? Is that really creating new data points for you? So
Yeah, one has to, yeah, it does create new data points for us. Because of, let's say the answer for whose beyond system happens and in the fourth sentence, it's going to move that particular sentence to the first one. Yes.
I agree to that, but is that like technically generating new data points? For example, the embedding, you are doing an embedding in data. So if you're jumbling up the sentence, is that suddenly creating a new embedding for you?
For the retrieval task, no, but for the extraction one, yes. Because the deep learning model will have different representation.
The start and end indexes are something that has been changed.
And what was the paraphrasing model that you would consider?
So we were considering Pegasus, but like it took like way too long for us to consider like doing it.
Actually, can you show me the fine tunes? So, for fine tuning, which model were you trying to?
So we were fine tuning on the given data set on the way of prediction. We can like generate false examples so that we can train a task one model. We also like extracted the start and end indexes of the answer, so we can find the task one model.
What was the last one?
So we used cross-interpret. Yeah, we used cross-interpret.
You were considering like a classification.
Yeah. So the task one was a simple classification. So basically classify a particular question.
For task one, you would.
Yeah. For task two, we were for task one like fine tuning. So for task two, we don't have the start and end indexes provided in the data set. So we create them by finding the answer extract in the correctness.
Do you have any metrics around how much improvement you saw after and before synthetic data generation?
No, I don't think we don't have any metrics.
And I believe the technique itself allows you to just look at quality answer question.
Yeah. Yes. We don't need to do anything extra.
Actually, we have two bits.
are present here. We are team 11 and we'll be presenting our solution on improving the domain specific QA. The problem statement revolves around the aspect of creating a knowledge base driven question answering system. Our approach broadly consists of two modules: a retriever that retrieves top tier relevant context for a given question, and a QA head that determines if a question can be answered, and if yes, what is its exact answer span.
First, we discuss the retrieval model. During the processing time, we use sentence transformers to recompute the dense embeddings of all of the contexts. Then, during inference time, we first get the embedding of the question. Then we use pairwise cosine similarity search spread up by types to get the top k context corresponding to that question. Now, in this slide, we describe the single most important contribution of our system. Paragraph level retrieval, wherein the retriever returns the top k paragraphs, requires k passes of the QA model. We improve upon this by proposing sentence level retrieval. So the top k retrieved sentences can be concatenated and fed to the QA model in a single pass. This allows us to train a much larger transfer model in the same inference time. So for the question answering head, we propose a simple transformer question answering graph, which takes as input the concatenated question and the context and outputs this answer as and end logics. Now, since we were required to run training within 12 hours without the use of any hardware accelerators like a CPU or a TPU, we came up with the incremental learning inspired solution. During each epoch, a particular data batch might be skipped with a particular probability P. This simple idea allows us to train on a dynamic sample of the data set without overfitting on any particular set sample. Finally, since all of our models were performing well within 500 milliseconds, we were able to run multiple models and get the best prediction as measured by the confidence score. This allowed us to, this simple assembly logic allowed us to get a significant boost in the performance. Finally, we use some runtime optimizations. Firstly, we use an one-line runtime, which is specially optimized for inference on CPUs. And secondly, we used caching, wherein a previously answered question can be directly returned without having to rerun the QA model.
One of the critical problems in this problem statement is to generalize the model to unseen themes. Hence, we experiment with several domain adaptation techniques. Contrastive learning is used to learn a generalized representation of answer and non-answer tokens. This representation causes robust adaptation to unseen themes. Using contrastive learning with QA loss leads to a 4.6% gain in squad F1 score while maintaining the binary classification F1. Meta learning learns high-level features by treating each theme as a separate task and minimizing the training loss over each task in the training set. This enables the model to fine-tune to a new task with minimal training examples. At test time, we fine-tune this meta model for each theme separately. Meta-learning algorithm RevDive achieves 6.6% on classification F1 and 2.7% boost in squad F1. We considered continual learning to tackle the catastrophic forgetting of a language model. Due to low forgetting in our model, it does not show much effect. We also used federated learning by iteratively updating a global model and some theme-wise models. Theme-wise data is simulated by clustering similar themes together, and the global model is later updated by averaging the weights of these theme-wise models after each epoch. We also tried synthetic data generation using generative models like T5 and BART. These experiments did not yield the expected results due to low quality of the data generation. To improve the quality of the data, generated data, we also tried generation from large language models like GPT-3 by careful prompting and trying over 100 prompts.
So this was our final approach, but we also tried several other experiments. Like for passage retrieval, we use DR2, which uses TF-IDF embedding for passage retrieval.
it is supremely fast and also efficient, but it fails to understand the semantic meaning. Then we use DPR, which uses dense embedding and understand the semantic meaning, but it increases the latency. Another promising approach was to combine the paragraph level and sentence level, but it also increases the latency. To arrive at our QA head, we tried several transformer models, and finally we chose BERT medium and Electra small for our experiments. For the unanswerability of the question, we tried read plus verifier approach, wherein we trained a verifier over the entire data set on the top of the QA head, and the QA head was only trained on the answerable questions. For fine-tuning tasks, we added some random weights to the random noise to the weights of the model to avoid overfitting, and to further reduce the inference time, we tried quantization, wherein we converted the weights from floating point 32 to integer 8. Now, coming to the results part, so we can summarize all our experiments into 4 broad categories. So, to achieve a latency of 200 milliseconds, we tried DRQA plus TFID and electrosmall. And the best approach under the 1 second constraint was ensemble model of BERT medium and electrosmall along with dense plus fast retrieval. If we remove the training time constraint, then the reptile version of this ensemble gave better results. And if we remove all the constraints, then span BERT gave the best results. And let me clarify you, all of this training is done on CPU only. So these were some of the challenges that we faced and tried to overcome. Thank you. This was the presentation.
If you would like to. That presentation is over. The Q&A.
It's the start of the pattern. That's in the Q&A. Oh, Q&A.
So this is like a demo website that we made. These are the bots that we made. Just look at any one of them.
Like anything random that should not be. Yeah, let's go back to the sure.
Yes, this is it.
Yeah. So you mentioned that in the retrieval step you are not doing paragraph, but instead doing that over sentence. For example, if a question is answerable by multiple sentences, and then can only be answered by multiple sentences, how does that work?
We observed that in the data set this was not the case. For in the squad at least, it is answerable by only one data set. But if we have reason to believe that there are multiple sentences, we can simply do a diagram kind of idea where we use 4 sentences per together. The idea is still science. All we are saying is that break up a large document like a paragraph into smaller chunks called sentences. Sentence does not necessarily one sentence, 2 sentences, depending on what they use.
And why would you want to do that? A paragraph to sentence.
Oh, because 4 reasons. One, you can reduce the number of passes of the QA model. That is the major point. So if you have 10 paragraphs, as you know, there's a 5 character limit in Perl. So you cannot concatenate multiple paragraphs and do one pass. So you will have to increase the number of passes to k. Right? If you use sentence level, you can concatenate all of them to one pass. That immediately makes your decrease the inference time a factor of k. So you have a much better model for one paragraph. That is the first reason. The second reason is when you are using a based retrieval or dense-based retrieval, a lot of the paragraph might be redundant. It's just that one small sentence in paragraph has the answer. So by reducing all of the unnecessary material, we are also improving the performance of the QA model by reducing the amount of information, just the proper signal.
Your recommendation is based on the word model or how
yes.
So you are, I guess, you're doing a recommendation sentence and doing that search on top of that. How are you doing a recommendation?
So in the retriever, the embedded is a generated using sentence transform. In the dense retriever, in the DRT retriever, we of course use KFI. Right? And in the QA, of course, you use smart.
You are using both these parts and the
yes. One second. So there are 2 solutions. If we want an inference time to
one next implemented in the
in the notebook it's the best of all.
And how about those who didn't get?
So, can I add? So, I think so the ensembles was over like the encoders and the dense that we're talking about, that is for the retriever. There's no ensembling for retriever.
Yeah. Retrievers for the human to QRX.
And I believe the meditation you are doing it for machine learning to I think limited meditation which are different.
Correct. Yes.
We had a context last term.
So yeah, can you just quickly show the method for that?
Data sets.
This is what is it? And I just wanted to see if this is helping you the contrast.
Absolutely.
So this is not helping you when you say binding explain.
Right. So when we say binary F1, we need the answerability. Okay, so there is a little bit of ambiguity in the PS. There is one answerability score and there is one paragraph score in which you correctly identify the paragraph. So for this, we find the binary F1 to go ahead.
Thank you.
2, 1, begin.
Morning. So I'm presenting our DevRev attempt for team number 47. These are our team members. Unfortunately, my co-presenters could not be here today since they had to stay back at the last minute for their ICCB performances. So I'll be covering for them. Now, I'll go on to our methodology for how we attempted this problem and move on to our final pipeline. The first sort of task that we worked on was team clustering. So in an attempt to sort of fine-tune models for different teams, we took several themes from our training data and embedded them using word-to-vec and attempted to perform k-means clustering on them so as to reduce the total number of models that we have to train. And while this did lead to some decent results, so we got sort of things like FC Barcelona and FC Arsenal, for example, were in the same sort of cluster. So we had reasonable clusters. But in the end, we still ended up dividing our training time between multiple models. And we did not within the given training constraints, we didn't see a measurable performance increase from doing this approach. While this could be useful for embedding theme-specific information into the model, it's not wasn't really feasible within the 12-hour training limit on a CPU. So the next innovation that we worked on was using a joint probability embedding for predicting our answer indices, where this is a relatively novel technique, where instead of assuming that the probability of the answer starting and ending at a given position is independent, we model the joint probability directly. This alleviates several issues such as the model picking the start of one answer and the ending of another answer and leading us to overall a completely senseless result. And while this did lead to some performance improvements, the training time was not sort of feasible within 12 hours since we inherently changed the semantic interpretation of the model's output, so it requires significant amount of retraining to keep similar performance. However, as these results from the paper, you can actually see that they did sort of get significant performance improvement from this approach. Now, the third methodology that we tried, which is made into a final approach, was modeling question similarities. So, in an attempt to recognize that some questions could have been answered before, perhaps phrased slightly differently, which was actually the case in several sort of training examples. We embedded these. Our approach was initially to use the Annoy library, which has been developed and maintained by Spotify, so it's scalable, to compute similarity distances between our word-to-vec embeddings. However, there were several issues with this approach, primarily being that Annoy does not support different similarity metrics, where we wanted to use the word mover distance, which has a much better understanding of the semantic relations between texts than things like cosine similarity, for example. The other issue was that it does not, it generates static data structures, which does not allow to ask and insert questions as we done our model. So we use a more standardized NLTK approach, but where it allows us to use word over distance to compare our questions. And this did reduce our inference times quite a bit. And it's still a static data structure, but we were able to get some performance improvements. So moving on to our final pipeline, our approach was first to match questions against the sample question answers using the word over distance, as I had described previously. So the data set used specifically for that is the sample data set that was provided to us before, since the data structure generated is static. Now, to predict question answers, we subsetted paragraphs from the same theme as the question, and we used a word mini model that was pre-trained on Squad V2 for this probability estimation. Now, in an attempt to reduce our inference times, we concatenated the paragraphs. So, since they were typically of only 100 or 300 tokens, whereas our model could take up to 500, this did lead to significant performance improvements, but there was enough of an error in recovering the paragraph indices, since the tokenizer does not recognize words in the same way that we do. And so instead we sort of scrap that approach. And so our final that's sort of how our final pipeline works. If these are the results that we got, so we sort of
traded off our inference times for significantly improved F1 scores from our previous sort of models. So we tried different approaches, including training our water models as well as BERT Mini and BERT Tiny. Those were the ones that we actually fully trained our dataset on. So we felt that this BERT Mini approach on Squad P2 was the best trade-off between performance and accuracy, where we got 49.53 F1 score on the training dataset and still on an average of 2 seconds per question. Of course, this varies with the teams. So some teams were finished within around 1 to 1.2 seconds, and some teams took up to 4.3. There were several sort of learnings and other things that we could improve on during this. Specifically, there was a lot of exploration going into balancing lightweight models with the performance that they sort of give, as well as looking into specific sort of non-deep learning approaches to estimating word similarities and question answering approaches. And we attempted to use several new concepts from literature. One was the joint probability approach that I had expanded on earlier, and where uses joint probability directly. And another analysis we attempted to do was analyzing the position bias within our models. So where typically in several cases it has been observed that models are when the answer is within sort of specific span of the context, say the PS question, models are typically biased to answer in that specific section of every paragraph. And this does not obviously scale well to different questions, since if the question answer lies much earlier, they don't really perform as well. However, the training time on CPU was not really enough to sort of dive very deeply into this approach. But we think it would make a significant performance improvement if done on a much larger scale. Thank you, and I'll be taking any questions that you may have.
Can you go to the joint probability?
Right. So typically, what models do is they estimate vector for the probability that the answer starts at one of, let's say, 10 to 512 tokens, and another vector for when the probability answer will end at another 512 tokens. So, and the way that probability estimation works therein is that we take the product of these two vectors to sort of a Cartesian product to generate what is the probability of the answer starting and ending at a given sort of pair of positions. Now, this has the issue that the model will sort of say that it's very likely for the answer to start here, but it's very likely for the answer to end somewhere else, and sort of it would end up combining two different answer spans into one sort of larger text. What this paper approach suggests is that we directly compute a matrix as a joint probability, so 512 or 512 matrix, where each index is the probability that we only take the upper triangular matrix for this. So that each index is the probability that the answer starts and ends at the corresponding column and row indices. And so since we're directly estimating the joint probability here, we don't really see the issue as much, where, for example, the answer started at one answer and ended at the ending of the other answer in the same sort of span. So we get much more succinct answers, and it does lead to measurable performance improvements in both F1 score and exact match.
What's the improvement again?
So these are on the from the paper itself. We actually weren't able to train this model since it changes the semantic interpretation of the model's output. So that requires a significant retraining of the model itself, which really wasn't feasible to do to like a very large extent on 12,000 CPU. We attempted this approach, but we didn't really get above like 10 or 12 F1 scores.
And this is the final implementation that you are not doing the joint probability.
No, not directly.
It's like an independent group.
This is an independent sort of resource that we directly trying to and see if we can make it.
And sorry, I think I missed how you are doing question generations.
Question, sorry?
Are you doing any question generations on your
So we did use a BERT model for a recurrent BERT model for question generation. However, we found that the accuracy was not like exceedingly high. So I mean, they generated reasonable sort of synthetic data, but compounded with the fact that we already have around 70,000 training points, and adding to that only increases our training times. And not only that, but then the additional data is not guaranteed to be completely accurate. We did not use the synthetic data that we generated.
And you eventually decided not to doing it. I guess you mentioned about this time.
Yeah, so we did attempt to do team-based fine tuning, but the iPhone scores that we got as a result, combining from multiple models, was not really comparable to just training one model for the entire 12-hour duration. As opposed to we attempted to do 6 different models on 6 sort of clusters of themes. So the clustering was an attempt that we to see whether we will be able to sort of identify different themes that we can train on, sort of clusters of themes, and fine-tune a model for each cluster. While we were able to fine-tune models that worked reasonably well, they didn't perform as well as just one large model. So we used a larger model instead. Okay, thank you.
Ready? 3, 2, 1, begin.
Hello everyone, a very warm good morning to all of you. We are Team 25 and we are here to present our work on building an efficient and easy to deploy question answering system. So what happens if I ask you a question again and again? You will get frustrated after some time, right? It's pretty common. So for a company whose customer asks them repetitive questions about a topic, it's pretty handy for them to have such a system which not only answers questions which are answerable from a given context, but also filters out those questions which are not answerable and routes them to a human employee who answers them effectively.
So for a problem statement, we have narrowed down it into three parts. First is the paragraph retrieval, which is essentially mapping user queries to the most relevant context in the knowledge base. Second is the answer retrieval, which is essentially predicting if the query is answerable or not. And third is minimizing latency and creating space efficient models.
Okay, so before we deep dive into the complete architecture, let's take a brief overview of the entire pipeline. So the entire pipeline is constituted by three segments. The first segment is the synthetic data generation, which is done using data augmentation and is further branched out on the basis of similarity thresholds. Second, we have paragraph retrieval. Paragraph retrieval is done using a combination of two algorithms, which is BM25 and cross encoder. The output of these two algorithms is then passed into a retrospective reader, which again constitutes of two modules, which is the sketchy and the intensive module. Again, to summarize the pipeline, we have data generation, paragraph retrieval, answer retrieval, and some other external features about the architecture that we have also implemented, which include latency reduction, accuracy time score analysis in a short time span. To get a better overview of the synthetic data generation, as I have told earlier, we have implemented data augmentation. Let me explain to you the entire pipeline. We have a list of paragraphs. Those paragraphs are passed through an analytical library to obtain a list of reduced paragraphs, or so-called reduced corpuses. These reduced corpuses are then broken down into words, which are passed through tokenizers to obtain vectors. Again, after passing those vectors to the label coherency module, we obtain a relation between them. Based on this, we have answer tokens and question tokens. The answer tokens are filtered out, and the question tokens are passed through the English pipeline to get final question answer pairs. That has been done using data augmentation. Now, comparing this data augmentation to more advanced techniques such as the GN, our technique performed better because we wanted more accurate answers in a short time span. So, the average time of generation per question answer pair was 2 seconds for our model, whereas for GNs it was taking 3.75. Also, comparing to a BERT large architecture which generated question answers, the F1 score generated was 0.8.
Okay, so let's take a deep dive into the retrieval mechanism. Firstly, we'll talk about paragraph retrieval. In paragraph retrieval, we firstly map every query with the synthetic dataset produced using the cosine method. If the similarity is greater than a particular threshold, the question answer pair is passed on as the output. If not, then we move on to the paragraph retrieval algorithms. The first of which is the BM25 algorithm. The BM25 algorithm ranks every document as per a DF-IDF algorithm. Then it gives out the top 10 paragraphs which are moved on to the cross encoder. The cross encoder is a neural network architecture which has 6 layers and is trained to catch the context out of the paragraph and the queries. It gives out top 3 paragraphs which are then passed on to the sketchy module of the retrospective reader, which will be discussed later in greater detail. The sketchy module actually passes an initial judgment which tells us if the paragraph is answerable or not. Now moving on to the answer retrieval segment. In the answer retrieval segment, we implemented retrospective reader. The retrospective reader has 3 main components, which are sketchy reader, intensive reader, and real verifier. The sketchy reader makes an initial judgment. What it does is it embeds and tokenizes all the corpus. Then the tokenized corpus is passed on through a transformer, which gets us an interaction layer. Through the interaction layer, we obtain logics that decide whether or not the question is answerable or not. We move on to the intensive reader. The intensive reader verifies the judgment made by the sketchy reader. It actually gives us 2 things. Firstly, the span and the score if the question is answerable from that paragraph or not. Then the third module is real verifier, which actually combines the score of the 2 modules, sketchy and intensive reader, and finally gives us whether or not the question is answerable or not. So now this is actually the complete pipeline of the retrospective reader, which I just explained.
Now, one might be thinking, what other features could we have implemented to, check into the latency reduction, time score analysis, and other features? Some other features included architectural changes. These architectural changes included naive implementation of a deformer. What is a deformer? Deformer is basically a broken down version of a transformer, such that you have a different architecture on a different model. For example, we have a Rockotta model trained on an Electra architecture. This is the implementation of a deformer. Apart from that, we have used transformer compression, which constitutes of quantization and unification.
Now let's take a look at the results and runtime analysis. Here we can see from this graph, we have tried to map inference time with different combinations of pre-trained Electra model for the sketchy and for the intensive model. And we found out that for the small combination, we are getting the lowest inference time.
And moving on to the F1 scores, here we can see from this blue line represents the F1 score, and they remain pretty much constant as we move from the smaller models towards the larger models. But if you take into consideration the inference time, it drops down exponentially, as it can be seen from the results. And for the fine-tuning part, we all know that it's useful to some extent, but it can distort the pre-trained weights, and the fine-tuned model can underperform than the pre-trained general model if the training data is not sufficient and the training time given to fine-tune is not sufficient. And also, one of the major reasons why we haven't used fine-tuning is the trade-off between the cost and the F1 score is not really worth it, because it defies the main goal, which was to build an efficient system which is easier and cheaper to deploy at the same time.
Also, to check into software as a service, we have deployed a Discord bot on our Discord server for paragraph question answering. Thank you. That's it from us.
If you have any questions, then
Sure. That is one of server.
Okay, so yeah, that's how we were doing that. Again, I will be using and we will tell the presentation is from here like and can you just explain the retrospective video that we got?
So basically, in the retrospective reader, we have three modules. The first is sketchy. Actually, the retrospective reader is kind of similar to a human. It first scans through the document and then makes some initial judgment and then rescans through it with deeper insights, right? So what happens in the sketchy reader is firstly all the corpus and the question, they are tokenized together and passed through a transformer where we obtain an interaction layer. Right? In the interaction layer, we have a CLS token, right? So, from the CLS token, then we obtain logis if it's answerable or not, the score is obtained. That score is kept aside, and we move on to the intensive reading part. In the intensive reading part, it again reads it. It again we have other model which again obtains an interaction layer, and it's trained to provide us with the starting end probabilities. And we also have the it also gives us the span.
Does it self-attention
Yeah, it does. We have the self-attention layers in between, right? We have actually there are two modules. The self-attention is employed there as well, and here we have self-attention and multi-headed cross-attention. Basically, there was this choice, and we moved on.
So basically, what happens is the sketching module focuses on the self-attention part for one of the aspects, and for the intensive module, we have a multi-cross-headed attention.
And again, I think you two chose against fine tuning. What? You two chose to be against fine tuning.
Yeah, wait. Yes. The trade-off kind of thing.
The trade-off basically was fine tuning. It requires more computations, it is more computationally intensive, and if we could have a corpus so similar to every other feature, so basically generalizing everything else. So if we generalize those features and to get a better answer, that is more less computationally,
not specific, because you are considering that also.
And did you do try fine tuning?
Yes, we have tried fine tuning. The fine tuning showed the results.
So being in the constraints, right? We reduce the epochs and alter the learning rates to lessen the time, and these were the results we got.
So fine tuning for a particular theme actually gave more inferences time as compared to a normal theme, particular normal generalized theme only. So that was what our inference was, and approximately 20% improvement in the overall architecture.
20%?
20%.
You guys think that right now you are getting 72%.
No, right now we are getting this. So right now
was a specific.
Yes, this is for general.
Ready? 3, 2, 1, begin.
So the given task is closed domain question answer. And the naive approach would be to take all paragraphs of the given context and answer the question for all the paragraphs. However, this is pretty slow, and since the QA transformer-based QA model are pretty big, we needed to come up with something better than this. So we followed a retrieve then read approach. So what do? Is we retrieve the top K paragraphs for a given context,
and then we apply QA on these top K paragraphs. Now this gives us an advantage that retrieving top K and then answering the top K paragraphs is faster than answering all the paragraphs. Next slide. So this is the pipeline. So this basically shows what are the different types of approaches we have tried so far. So we start with a context and a query, and then we pass it to a retrieval model. So there are three models, and we can use any three of them to get the top K paragraphs. And what we do then we answer the all K paragraphs using the QA models. There are multiple Q models, and we can use any of them. And then we return the answer and the corresponding paragraph with the highest score. Or we have tried one more thing, is that we take the top K paragraphs and then we use a zero-shot learning re-ranking model. We basically rewrite the model and then rewrite the retrieved passages, and then we use the top paragraph, and then we use our QA model to answer answer the query and return the paragraph.
Let us get an overview of the different techniques that we have used for retrieval. First is dense paragraph retrieval, which is a deep learning based technique, and second is statistical retrieval, which uses the statistical properties of the corpus to get the relevant documents. But this is a trade-off between speed and accuracy when we try to use these techniques. DPR tends to be much more accurate, while statistical techniques are much faster. Now coming to dense paragraph retrieval, the DPR technique, what it does is it trains the encoder using negative sampling. So there are positive question and paragraph samples and negative question and paragraph samples, and that trains the encoder so that it retrieves the relevant paragraphs and ignores the irrelevant paragraphs. And then we tried this Courtney paper. This Courtney paper further improves on this by using a novel pre-training approach. And finally, what we have done is the encodings. We take the cosine similarity between the question and context vectors to get the most similar paragraphs. In statistical techniques, the method is pretty simple. We create an inverted index and use TF-IDF scoring to get the top K relevant paragraphs. Using these techniques, we were getting a retrieval accuracy of about 75 to 80% for top one answer, top one paragraph. So we tried BM25 and some of its variants. Now, what we made an important observation that most of the answers were in a single sentence, and so why not instead try a sentence level retrieval instead of paragraph level retrieval? But there is a problem. The sentences may contain pronouns, and these pronouns will make the sentence unclear when we want to answer the questions. So first we need to apply co-reference so that we replace these pronouns with the proper nouns, and now we can apply the sentence level retrieval to retrieve the top case relevant sentences. Now, once we have got the top K relevant sentences, we will take the paragraphs corresponding to those sentences in our QA model. Now, Ananya will explain us that QA.
So basically, we tried different QA models, basically different variants of BERT like Roberta, Distill BERT, DBERT, Stanbert, BERT Multicase, and Electra. We tried BERT large models also, but due to the we didn't move ahead with them. So we found that Roberta and Electra gave us the best results. So there were certain themes given in the data set which were kind of similar. For example, Air Force, airport navigation, etc. For that particular things, we applied topic modeling also. For topic modeling, we used particularly LDA, and we came to know when the number of clusters are set as 8, that is what was giving us the most optimal result. So for 360 themes, we were having around 8 clusters. But we found out that particularly there is no local model performing best for any of the cluster. Electra was the model which was performing globally best for each of the cluster. So we didn't move ahead with this particular like local model technique because it was not improving our accuracy significantly. Now the thing is that there were certain questions or queries in the data set which were unanswerable. So we had to handle that particular thing also. So there were 3-4 approaches that we tried, but these are two approaches which were best for us. So first was the score-based threshold. So we marked the query as unanswerable if the answer given by the model had a less score than a certain threshold, and answer length-based threshold, we marked the query as unanswerable if answer length exceeded a certain length, right? So this is the graph for the score-based threshold. Here you can see we had a plot of density curve. So we had positive answer score and negative answer score. So we had a density plot, and we set the threshold at that particular point where these two plots intersected. So in case of Electra, that was around 0.1, and in case of the threshold was 0.1, and in case of Roberta, the threshold was around 0.2. And the average positive score in case of Roberta was 0.93, and average negative score was 0.01 in case of Electra. And similar scores were observed in case of Roberta too. These this is the graph for answer length based threshold. So basically, if you see where the elbow point lies when n equals to 15. So if an answer is having length more than 15, it tells like QA model is not answering the question precisely. Hence, that particular question is not answerable. So these are our basically evaluation matrices. Please know, like basically Electra was performing the best, and these are the different retrieval techniques which we tried. So this is Courtney plus Electra score is about 33.33 out of 45, which gives us a score of around 75 to 74%. QA score is 32 out of 45, which has a score of around 71%. So particularly we replaced Electra with Roberta because we got down our latency from 1.4 to 1.2 seconds.
This is a graph that shows the evaluation of our best model on the 30 themes. We have included both the para score and the QA score. You can observe that in these themes, the score is pretty high for both of the tasks. These are the ones in which there are both positive and negative questions. So, because we have applied the threshold correctly, the negative question, two negatives are chosen correctly and the score increases. And here you can see in some of the cases, the QA score is more than the retrieval score. This is because in some cases, there might be multiple paragraphs that are relevant for the particular question, and therefore.
So, yeah, thank you for your attention.
You can go back. The thing is that here, like we were considering that only a single paragraph was more relevant for a question, but it might happen that multiple paragraphs are relevant for a particular question, and in that case, the paragraph retrieved will be that accuracy will decrease, but still that paragraph, wrong paragraph might have the answer, so it will retrieve that answer correctly because the QA model is quite accurate and it will give you the correct answer. That's why the QA score increases.
Can you go back to the retrieval again? And then your paragraph is low good number of views. It's around 0.5 the paragraph that you guys showed. So basically the last page.
Could you go? Yeah.
So the paragraph scores are not that good.
Yeah. In this case, like certain cases where the mostly there this we observe that in certain cases the context were quite related. Like there were multiple paragraphs, but each of the paragraphs were closely related to each other. There were many sentences in common. So in those themes we did quite well. But in some other themes where that was not the case, like the context, the paragraphs were pretty independent of each other. In that case, the score.
Can you go back to the retrieval type?
This one?
Yeah. So you are doing a weighted average of these two models, retrieval models.
No. This is not, currently we are not doing any weighted average. We are just using a single model. No ensemble.
Let's show like what we have tried. So
Yeah.
from there we use one of them. I tried
Finally we use Cotming, and then here we use Roberta distill form. Like if these are the best three that we got, so we have put only these.
Well, I believe the retrieval is would have been better and someone would have.
Yeah, there, we wanted to put the ensemble, but actually in that case, the scores that we are getting from each of the models, in certain cases we cannot compare them directly. So we were not able to figure out the correct metric through which we can bring them to a comparable form and then use the weighted average.
Yeah.
Thank you. Jesus Serpes. Jesus Serpes.
Ready? Ready? 3, 2, 1, begin.
Good morning, everyone. We are team number 55, and we are going to present a solution of improving domain-specific QA. The modern QA systems have gained widespread attention thanks to large language models, and we aim to design an intelligent question answering system that can answer domain-specific questions in low resource and time constraint settings. Our QA pipeline consists of two components, which are retriever and reader. In retriever, we have used a single encoder architecture, which encodes all the passages into dense embedding vectors, which capture the semantic meanings of all the paragraphs. Then these vectors are stored in files. At inference time, the question is encoded using the same encoder, and top tier relevant passages for that question is retrieved, which reduces the space for the reader model. We experimented with various pre-trained models and various architecture, and we finally narrowed down to mini LM12 for a single encoder architecture. And for retrieval, we have used files for speed and efficiency. And as you can clearly see from the tables, mini LM12 gave the best performance speed trade-off with almost 0.82 F1 on top 10 and 0.91 F1 on top 20, with a mere speed of 30 milliseconds for collapse CPU. And here you can clearly see that from the figure that across all the pre-trained models, many LM12 perform the best.
Now let's talk about the reader part of our model. The first step in the reader model is synthetic data generation, just 3 steps. First step is answer extraction, second is question generation, and third step is round-trip filtration. Let us see how these steps work. Let's say that I have a context which says Google was founded in 1998. Firstly, I perform named entity recognition on it to extract potential answer entities from it. Then we highlight those answer entities in the context and feed it to the encoder of a sequence-to-sequence T5 transformer model. The decoder of this transformer model will output a question that corresponds to the context and the extracted answer. Once we have the question answer pairs generated, we perform round-trip filtration on them to remove the incorrectly generated question answer pairs. We feed the context and the generated question to a question answering model that outputs a predicted answer. We compare that predicted answer with our extracted answer, and if those answers don't match, we remove that question answer pair. Now, to ensure that the distribution of our synthetically generated dataset is similar to that of the real dataset, we also add unanswerable questions to it. Let us say that we have two different contexts that are from the same theme. Now, and we have also generated answerable questions for both of them. Now, the answerable question for context 2 can act as an unanswerable question for context 1. And we also filter out the false unanswerable questions, which is a classical approach that involves using TF, IDF, and cosine similarity. Now, for fast convergence and domain adaptation on unseen themes, we use meta-learning. Meta-learning is a simple training methodology which trains a joint model on two different tasks that are structurally similar to each other. Let us take an example to understand how meta-learning works. Let us say that I have two different contexts from different domains that have a similar structure. As you can see, Microsoft is related to Bill Gates in the same way as Beyonce is related to her father. Also, GitHub and LinkedIn would be related to Microsoft in the same way as Rumi and Blue would be related to Beyonce. We believe that a generalized model would learn to mask these named entities and learn the structural relationship between these two different contexts and map them to a space where their distribution would be similar due to their similar structure. Now, coming to the training part of our meta-learning model, firstly, the meta model is trained on all 359 themes as individual tasks and tries to generalize on all of them, but taking fewer epochs than a common global model. Then, once we have the meta-trained base model, it is fine-tuned on the synthetically generated data set of the 30 new themes that we are given. We observed that the meta-trained model is able to converge 5 times faster than a common global model by using a much smaller data set and using only 5 epochs on each theme. Now, we found two types of runtime optimizations. First one was model quantization, which speeds up the tensor operations by converting the 32-bit floating point tensors to 8-bit integer values. Second optimization is graph optimization of the computational graph of our model. Both of these optimizations are performed using the Onyx module of optimum library. And we observed that using these two optimizations, the inference time of our question answering models was reduced by approximately 30% on average. Let's go through a little pipeline step by step. First, we have entire data set. We break it down theme-wise into theme-specific data sets. Then we perform multi-threading to create a separate thread for each theme. So each thread works on a specific theme. Then for each theme, we generate a synthetic data set and feed that data set to our meta-trained model. Then the meta-trained model is fine-tuned on each theme and a theme-specific model is stored separately. Once we have a theme-specific model for each theme, we perform runtime optimization for that and then we perform inference using the retrieved passages from the retriever and the provided questions. Coming to the results part of our reader model, we evaluated a range of transformer-based models. BERT Mini 5 came out to be the overall best performer among all models. BERT Mini 5 is a compact transformer BERT-based model from Google. It has 4 attention heads and 12 middle layers. It has only 18 million parameters, yet it gives an F1 score of 86% on our validation set, while taking only 120 milliseconds after optimization to answer each question on CPU. To evaluate the results of our meta-learning, we trained the BERT Mini 5 model on synthetically generated dataset of paragraphs that are provided to us on 30 new themes. Then we evaluated that meta-trained BERT Mini 5 model on question answers.csv that was given to us as a subsample of ground truth. And we observed that the median F1 score for meta-trained model was 92%, which is significantly higher than the median F1 score of a BERT Mini 5 without using meta-trained, a common global model.
In the last, we'd like to thank DevRev for this interesting problem statement. We surely had a steep learning curve for the past month. We invested significant time and efforts to provide the most optimized and generalized solution for the problem statement. And in the view of that, we applied this meta-learning approach, which generalizes well across all the domains and yet gives better convergence on specific themes with great results. And finally, we have packaged all of our QA pipeline as a library. So therefore, our QA pipeline is modular, scalable, and at the same time deployable. And you can also use a plug-and-play functionality to configure parameters in the reader and retriever classes, and even give different models to try different approaches. Thank you.
I have a question. So you talked about model quantization.
Yeah.
Right. But my question is, does it really improve your training time, or like does it improve your CPU time?
It was not used for training time; it was used for inference time.
Even delivery impact, because quantization is clearly used for memory, not for the CPU.
Like, yeah, experimentally there was a slight reduction. From what I remember, the inference time of BERT Mini 5 before the quantization was around 180 milliseconds on each question.
And along with that, I have to add that we also added the graph optimization. We also did the graph optimization technique so that
Yeah, from 180 milliseconds, it was brought down to 150 milliseconds. It was not a very big reduction, but it was
more than
Can you go back? Okay. Was it able to get
No. We the question answer what CPR given to us at 14 keys. So this is basically a density plot of those 14 keys.
was it
92%.
92%?
It's the median of all keys of F1 score.
Let's go back to the generated data. So, before the meta learning, you were mentioning that it helps you improve for all things in general, right?
I mean, we only had 14 themes in question answer, so for those themes, it did work. You don't have the actual ground, right?
So your meta learning technique would require a previous set of question answer pairs, or you are also trying.
I mean, to train the meta-based model, yes, it would require a training data set, but once we have the new themes, it would generate some data.
You just have the paragraph, you don't have the question answer pairs.
For that, since we have trained a base model on a variety of corpus, and since using the meta learning approach, it generalizes across a theme, so we are pretty confident that it will be able to answer questions.
We are also generating synthetic data set, right, on those paragraphs. So, this one?
Yeah. So when you say round trip filtration,
Yeah.
So this depends on your question
Question
answer
answer.
model in itself, right? Okay, so isn't that a kind of a simple dependency or GFT?
Not really, because the question was that the model that we're using was Electra based. So on our training data set, Electra based is state of the art model. It gives an F1 score of around 90%. So yes, there is a dependency on this model, but if we're using a good enough model, we.
So you are suggesting that you can use a very heavy model to do this synthetic data generation?
Yeah, yeah, but because we parallelized the whole pipeline, and so we did the whole synthetic data generation in a very less time, and because of multi-threading and we did not.
It does depend on the model, but it is a fair trade-off.
I think so you are still in the process of creating a question answer model, right? And you are saying that you are using that same model to figure out if question can be answerable or not. So yeah.
For synthetic data generation and round trip filtration, we have used the Electra model, and for the our approach, we have used per 25 model, which we have.
Yeah, we use different models.
How we are doing the entity recognition?
Using the spatial library of Python, it takes only like 20 milliseconds. We also had model-based approaches to extract answers, but those took like 2 seconds or something to extract one answer.
And did you explore anything else other than hash or the notebook?
Yeah, I mean, we first tried the traditional approaches like TF-IDF and VM25, and then we also tried to use CTR where they had two encoders, but we needed something that was giving good performance at the same time giving us lesser time, so we tried Fires. We even for indexing purposes we used Annoy, but it wasn't giving much configurable parameters, and with Fires you can create your own index catering to the kind of data that it has.
Here you are only doing the first traversal is just doing a pass search for the domains and getting the log of them.
Yeah.
And I believe you do a re-ranking, right?
We don't do re-ranking because using many other model and with Pies we got very good accuracy. And apart from that, as we already told you, that BERT25 only takes 120 milliseconds. So we feed as a part of a pipeline 3 context with the top 3 context passages. So it gives a very good accuracy. And still we are able to get under 1 second. Less than half.
What happens if you ask a question which cannot be answered by any of the paragraphs? So when you go through that process.
But that part is in the synthetic data.
If
in that case, still it will read the topmost relevant paragraphs that I think would have the answer. So our data model, it is trained on the meta learning approach, and it will automatically, based on the confidence score, judge whether the answer is whether the question is answerable or not. We have set a threshold based on hyperparameters to read a lot of data sets.
Ready? 3, 2, 1, begin.
Good afternoon, one and all. This is Team 27. Today we are here to present our simple yet effective multi-paragraph question answering model, leveraging the powers of NLP techniques to answer the user queries in a flash. The overall pipeline of our model is as follows. So our model encapsulates a two-module architecture. The first one being the paragraph retrieval, and the second one is the answer retrieval. So if we begin with the paragraph retrieval, it basically takes the questions and the paragraphs as an input, and it retrieves the top two paragraphs using the cross-encoder and bi-encoder model. The output from this module is then passed on to the answer retriever, which basically takes the questions as well as the top two paragraphs retrieved from the paragraph retriever, converts them into the contextual embeddings, which are then passed on to the decoder as well as verifier parallelly. In the decoder and the verifier part, we basically predict the start and the end span probabilities, as well as we check whether the question can be answered or not. The output from this model is then passed on to the final component, which is basically the answer verification. So where we compute the actual answer for the text depending on the probability scores that we computed in the decoder and the verifier component.
The first task is to predict the paragraph in which the answer is located. We tried a few AI models to achieve this task, for example BM25, but these don't support semantic stitch. Then we tried a retrieval re-ranker pipeline. So the query and passages are passed to the bi-encoder, which basically uses a pre-trained language model to transform the passages and query into dense vector embeddings. These embeddings are then used with cosine similarity, and the top k potentially relevant passages are through experimentation, we found that retrieving the top 10 passages works the best. These passages are then passed to the cross encoder, which transforms the query and uh, each passage through a transformer network and uses a relevance score to return a ranked list of passages. The thing is that bi-encoder is efficient but less accurate, whereas cross-encoder is slow but highly accurate. To obtain the benefits of both models, we combine them by only passing the few top candidate passages retrieved by the bi-encoder to the cross-encoder. We found that retrieving the top two passages
yield better results than one, and these are passed to the question answering.
Now let's take a look at the question answering model. You can see that it's a very simple architecture, encode and decode architecture with the internal verifier and a final answerability verification model. So initially we pass the input, which is the text, the paragraph and the questions, to a tokenizer which matches with the encoder that we have chosen. Now the tokenizer tokenizes the text and then passes it to the encoder, which then outputs the contextual representation. The contextual representation is passed on to the decoder, which outputs the span properties, the start index properties and the end index properties. Whereas the pooled representation is passed to an internal verifier, which predicts the answerability properties. And both of these values, which are output by the recorder and internal verifier, are passed on an answerability verification, which checks, okay, if there is an answer, yes, give the indexes of the answer, or say just a no. Let's take a look at the loss function we have used for the function. We have used basic cross entropy loss for both span prediction and internal verifier as well. And we trained the entire model based on a linear combination of both. Right? And alpha 1 and alpha 2 have been using cross validation. And for answerability verification, the final module that we are using to check if there is an answer, we take in SDiff and SN, where SDiff is calculated from the probabilities of the span indexes. And the internal verifier gives us the SA. Now, what is SDiff? SDiff is calculated using the first index properties of the start index, start probability, start span properties, and the end span properties. And this is subtracted by the maximum possible prediction for span, which is the SI and J. And we have to make sure that I is less than J because answer has to be valid. And the internal verifier gives us the probabilities of does it have an answer or not. And we subtract that, and we use a linear combination of that to calculate a score called S naught. Now, as we saw earlier, we are using two paragraphs. Now we get the minimum of the two paragraphs score, which is the better answer. Now, if the score we calculate is lesser than the threshold, we have found through cross validation, then it has an answer. Else we do. Now let's move on to the experimental research we have done. So we experimented with the classical BM25 model and a deep learning by-encoded cross-encoded model, and we found out that the top 2 accuracy was significantly better with the by-encoded cross-encoded. So we proceeded to move on with the by-encoded cross-encoded for paragraph. And for the question answering models, we tried BERT, Albert, and Electra with all with internal verifiers, and we found out that prediction time were somewhat similar for all three, but the F1 score for validation was very high with Electra, so we had to choose Electra for the question answering model. Also, we also tried data augmentation methods like burn and augment to replace the words of the dataset with synonyms, so that we can improve the diversity of the dataset as well as the strength of the model. And also, in the case of improving optimization, we reduce the word token max length from 512 to 384, so that the inference time will decrease. And also, we also found out that the most of the paragraphs in the dataset were around the max length 350. So the combination of question plus paragraph won't go more than 384. So we fixed on that. So that improved a lot in terms of time. And talking about fine tuning, we actually fine tuned the model on Electra, and we were not able to find much significance better than this. But because maybe the themes were lesser than questions for the themes were in 40 that compared to 30 theme paragraphs. And thank you for your attention.
We used both. We used multi-Q and
multi-QA as by-encode and for cross-encode we use DevRev. Did you try any other? Sorry? Did you try any other? Yeah, we tried multiple, we found out
the best way.
Can you go back to the cross-encode slide? I think there's a reply.
Yeah.
Actually, already submitted. We saw.
We tried that fine tuning for, but we were not able to find significant improvement when coming to global model and fine-tuning it. So stick with the global model.
So there, the other practice to go after log p y.
Yeah.
No, inside also there is one more step. The log of p. Yeah. Will be a. Yeah. Wherever you are taking log.
Yes. And with answer to the question, essentially, you go through a paragraph for that period, you figure out it. Sorry, whatever generated answer we get, we do verify it.
Verify. Here the beta 1 and beta 2 are variables or either?
No, they are not parameters.
Like violation is set to be found. From violation is set to be found. So you need a tuning and then. Yeah.
So this doesn't have I guess so did this improve your unanswerable
Like we tried without the internal verifier, but with internal verifier improved F1 score about 2%.
About 2%.
2%.
And can you go back to the here we are not doing any production technical, not behavioral technical.
No. Instead of the first part, the retrieval part, we could use VM verify other retrievers, but we don't use the semantic. So we stuck with the line.
What's the mode of dependency you're using?
For electra, this is
The what dependency you're using? The average. What's the so you might have tried something else in the retrievers. Maybe they're not from multiple areas. I think that is pretty close than what was required, right? And then is there something that we use while because midterm had yeah.
Ready? 3, 2, 1, begin. Okay, so good afternoon, everyone. We are team number 61. So we will be discussing about synthetic data generation, model training and its analysis, and hyperparameters used for fine tuning, and how we optimize the runtime, and hence concluding with the results. We aim to build an optimized machine learning model, which is based on question answering, which effectively gives accurate answers in minimum time. For the research part, we evaluated and considered many pre-trained models like Albert, Distilbert, etc. Next, we focused on synthetic data generation using restriction and using external data sets. And next, we integrated tokenizers with their respective models. And lastly, the fine-tuning was done on the word-based case using the generated data set.
So as mentioned, we had a limitation in data, so we generated synthetic data by halving each of the data points. This helped us reduce bias as the number of paragraphs with no answerable answer increased. This also helped the trained model to be more inclusive and fair. For dividing this, we used Node.js and we created a dictionary-type data structure. This also helped decrease the retrieval time. So I'll walk you through an example. Here you can see that this is a data point. For dividing, we found the midpoint and using the nearest full stop, we divided this data.
So let us walk through the model part. So our model is an attention model based on the transformer architecture. Attention model basically does that it finds the sequential as well as the emotional relations between the words in the paragraph. Then there comes an important term while we are talking about the attention models, the number of heads or the attention heads. It is an attention model that determines the number of parallel attentions between the input sequences. We also know that by increasing the number of heads, the input, the time as well as the accuracy or the performance increases, and vice versa. Here we are having two models, model 1 with number of heads 12 and model 2 with number of heads 8. Now let us walk through the training analysis part. So this is the initial model. This is neither fine-tuned nor trained on the given dataset. We can see that there are two color dots. One is the red dot, that is the question answer pair, which is not answerable. Then is the blue dot, which is the question paragraph pair, which can be answered. We can see that the concentration of red dots in the below part is very high, and the concentration of blue dots in the above part is also high. This shows that our model is giving correct answers with a high accuracy and the non-answerable question answer paragraph with a very low accuracy. But that's not a valid graph that we actually want. Now we are having two models, model 1 with number of heads 12 and model 2 with number of heads 8. Here we can see that the red dots, which is the data points which cannot be answerable, is less in amount at the upper part of the graph. But whereas in the model number 2, where the number of heads are 8, it slightly increases. So it shows that there is it's the confidence scores. So we can see that it slightly increases. There is a trade-off between the accuracy. It's the number of questions. The question paragraph pairs that. So here becomes the training loss part. We can see that the fine-tuning part, the slope is gradually decreasing, which is actually a good thing. We can see next part. Then comes the fine-tuning. We are having three hyperparameters. One is the learning rate, then weight decay, and there is number of epochs. We have fine-tuned our model sequentially. First, there is a learning rate of 10 to the power minus 5, then weight decay of 0.1 and epochs 0.5. And gradually, we decrease the learning rates as well as the weight decay. We can see that both the two models, model 1 with number of heads 12 and model 2 with number of heads 8, the training loss decreases gradually. That's a nice part of a model.
Okay, so here comes the runtime analysis. The model 1 where the number of hits was greater, that is 12. It took about 400 milliseconds for making a correct prediction. But in the case where we reduced the number of hits to 8, it took just 70 milliseconds, nearly reducing the prediction time by 5 times. As we have seen in the last slide, there was a slight trade-off. The second model had a certain bit of reduced accuracy. So we had to trade off a little bit of our accuracy for this huge significant improvement in the prediction time. Okay, so here are some examples stating the fact that I just stated. So as you can see, for the first question, our model predicts the correct answer with about 99.7% of accuracy, but it takes a time of about 400 milliseconds for making this prediction. Whereas in the second model, where the number of hits were reduced, it predicted the correct answer with a slightly less accuracy, that is 95%, but the time it took is significantly reduced, that is of the order of 70 milliseconds. Okay, so this is the basic pipeline that we employed in our prediction model. So as soon as we feed a question paragraph pair to our model, we cannot actually directly feed the text to the model. It has to be tokenized. It has to contain the positional embeddings. So we had to pre-process our data and convert it into certain set of logics, which were then fed to our training model, which was bird-based case. And the output that model generated was also in the form of logics or tokens, which had to be post-processed or decoded into human understandable text, or what we call the predicted answers. So these are the main key points. We had to trade off a little bit of our accuracy for significant or huge improvements in our prediction time. We employed a technique of synthetic data generation, which instantaneously doubled our data set, and as we were not allowed to take any outside data sets. Also, we designed algorithms so as to integrate our input pipeline with our model. Also, hyperparameters. We trained some of our hyperparameters for better results and reduced prediction time. So I thank you on the behalf of Team 61, and we are open to questions.
How did you figure out the hyperparameter? That's a benefit. Experiment. Hold on to that. Was the loss function you were using here? Yes. What the loss?
The loss is training loss is here 0.0 and here is 0.04.
What the loss function?
Loss function it was added.
That's not
Okay. Loss function basically we use a previously existing function trailer that computed the loss. It is a word-based case. We just fine-tune on the given data set. That was synthetically generated.
Probably will be getting some loss.
Yes. X-axis are the number of questions that a question paragraph pair which is not answered. It's question 1, question 2, question 3 and goes on like this.
Question index.
Yes. And on the y-axis is the confidence scores.
Like this only tells that when the number of hits were more, the model's accuracy was quite good. Like it was predicting wrong answers with very low accuracy. But as
the point on the left hand side of this graph, when x equals to 0,
yes.
What does that represent?
It actually represents the first, like the predicted answer for the first question.
Yes. Since the data points are so much enlarged, we see that there are many data points on the line by x equals to 0. But it is not that.
So my question is that what is on x-axis?
Number of indices of questions.
Okay, so it's like irrelevant.
Yes, it's irrelevant. Just the y-axis. Okay. Yes.
What does this y-axis represent?
Okay. In the y-axis, if suppose this is the point that the question paragraph pair, which cannot be answerable, it is showing that the model has predicted an answer with the accuracy of this much. Suppose it is 0.7. 70% of accuracy, by 70% of the confidence level, the model is predicting an answer which should not be there because it's not answerable question.
Along the y-axis,
Basically, if it's like showing, it is predicted some answer and it is saying that the model is 95% sure that it has an answer. So if the points are nearer to the top axis, it shows that it has predicted an answer where it should not have predicted an answer.
Yes.
So in the first one where the number of hits is 12, we can see that there is no like lesser concentration of points.
Yes.
In the when the number of hits is 8, we can see that there are numerous points. So it shows that when we decrease the number of hits, the answers were predicted where it should not have predicted the answer, and the model is quite confident that it has predicted the right answer.
but this is the minimal trade-off that we had so as to reduce our prediction time.
Again, retrieval pipeline. Is this the retrieval?
No, that's
This is the
not.
final model.
This is the just when you are giving a question. Like if there are a number of paragraphs, we generally create a dictionary of a theme, all the paragraphs related to that theme. And when a question is given, related to that theme. We find all the paragraphs, and we find the answers of that question in all the paragraphs, and we check. And then with a given or experimented threshold, we find that if the confidence score is above that, we consider the answer. Otherwise, we reject the answer.
So that obviously has a lot of latency.
Yes, it is around 100 to 120 milliseconds.
That is given per paragraph.
Yes, per question. If you giving a question, there are multiple paragraphs that can be there, right? So for that question, it will check all the paragraphs and find the answer. In that time is 100 to 120 milliseconds.
In that time?
Yes.
So you are saying that you take a question, you go through each paragraph and see if it can be answered.
Yes.
So you are saying that it takes around 1.2 milliseconds to figure out if a paragraph can answer question or not.
No, 120 milliseconds.
So you are not doing a retrieval, right?
No, we are not doing any specific retrieval. It's very general.
The time is very minimal. Like the thing we were doing with Node.js, the dictionary creating part and everything, it is very minimal compared
That's
to
very
this.
minimal. But while giving the paragraphs to the model, all the paragraphs to the model, it takes around 120 to 100 to 120 milliseconds, and model takes 60 milliseconds or 70 milliseconds approximately to find the answer. So overall time, you can see it's around 180 to 190 milliseconds of giving a answer to a one question. If it is given, it will find all the paragraphs, find the question answer to that question in all the paragraphs. It will take around 190 to approximately 180 to 190.
We are doing an parallelization of that sort.
No.
So that, okay, for example, if we have one question,
Yes.
so this latency will increase the number of paragraphs given from the order of 1 lakh.
Yes, that. But that can be improved by if we are able to create data loaders of that, so that it parallelly gives the.
So, but did you sort of try to first figure out if a paragraph is does make sense to actually ask it to work out?
Sir, we did actually try that, but we didn't come up with a very efficient algorithm. That was the only algorithm that we find that could be used, because then, when we see that there are paragraphs, the paragraphs are very less in number. In that sense, we tried this one. Bird-based case, and we have fine-tuned it on the given data set, which was synthetically generated by splitting the paragraphs into half. We are going to the middle of the paragraph and finding the nearest full stop, so that the sentence doesn't reach. The complete sentence is there in the paragraph. And we are also changing the start index and the answer possible part in the paragraph.
Okay. So do you also do any sort of tone branding while dividing the paragraph?
No, sir. We don't do such.
And I think we are not doing any sort of fine-tuning.
We have done fine tuning on the given data set, or both the data sets.
Not for the thing.
Not for the particular. It's a global.
You are running this.
Yes, on the CPU. It's a CPU model. Thank you.
well created.
Ready? 3, 2, 1, begin.
Greetings, everyone. We're here to present our solution for the very specific question answering pipeline. Involving retrievers, readers, and answers, as well as some model heuristics. We aim to provide a fast and accurate pipeline with domain adaptability, as well as efficient user validation. The first stage of the pipeline handles the paragraph retrieval task using an Elasticsearch-based main retrieval, as well as a cross-encoder to re-rank the top 5 passages. We employ both theme-specific as well as global rankers, and we then pass the ranker scores as well as the time left to a novel heuristic which determines the number of passages to be passed to the reader. Then finally, using the confidence score of the reader as well as the ranker scores, we predict the answerability of the question and output the answer accordingly. So the BM25 after the effective first level filter, we are able to narrow down the passages from 700 to the top 5 within 60 milliseconds with an accuracy of about 95.2%. So the rankers are essentially cross-encoders trained on query passage patterns along with the semantic similarity. And here we outline the different effective use of retriever ranker combinations. So to train our ranker, we use knowledge distillation, where we try to minimize the MSC loss between the student and the teacher model, where our student model and teacher model are based on media level. So we see that upon fine-tuning on the given data set, we are able to match the fine-tuned model. We are able to match the accuracy of the fine-tuned model with the pre-trained teacher model while being around 3 times faster. So we also explore the use of contrastive loss training for the rankers, where minimizing the loss translates to simultaneously maximizing the positive pairs, similarity of the positive pairs, as well as minimizing the same for the negative pairs. So here the negative pairs are the hard negatives that are retrieved by the BM25. And we see that the improvement in the ranking results is not as pronounced as in the case of knowledge estimation, so we carry on with that. So finally, upon fine-tuning on specific themes that have enough training examples, we see that there is a considerable improvement in the ranking accuracy. So we are actually loading two theme-specific rankers during in our pipeline that are loaded on runtime.
Alright, so now that we have taken a look at the rankers, let's focus on two observations. Firstly, that from the ranker's perspective, not all questions are equally difficult. And the time constraint is applied on the average time taken to predict answers for the team. So we found that passing multiple passages to the reader instead of or lighter reader instead of just passing the top passage to a heavier reader usually performs better. So we can see how we'll use these ideas to vary the number of passages passed to the reader so that difficult questions can be prioritized. So here we do that first focusing on the expected number of questions solved by a model. So we can look at that as a sum of product of these two probabilities. Here P of x comma I is the probability that the answer lies in the top I paragraphs of a ranker, and K is just the probability that the reader will solve the question given the model. So here Zi is the number of passages that are actually passed by a model to the reader, and so the constraint is that sum of Zi is bounded by some constant K. So this is an optimization problem and the optimization variables as well. So for predicting the probabilities P, we first we observe the ranker scores. For example, if a ranker scores 0.9 for the top paragraph and 0.2 for the second paragraph, clearly just passing the top paragraph will do a good job. So you can just, based on this insight, we can take X as the concatenator vector of the ranker figure scores, and then we can train a neural network to get out the C of the probabilities. So then we go to the actual optimization algorithm. First, we initialize all CI as one, so we are just passing one passage to the question, and then we can really implement the CJ variable which locally increases the expectation by the maximum. So we can also follow this with a random algorithm where we repeatedly choose several indices of Z, just increment them and then increment them using the same, following the same value operation. Then finally, we can also think of A as a dynamically changing variable based on the time depending on the average reader latency. we can be following results that if you just naively pass the top two paragraphs to the reader, then you get an accuracy of 0.854. Compared to the use our approach, then you get the accuracy of 0.85.
Yeah, so we use transformer-based readers here, which have stacked encoders and decoders, and we predict the extractive answer span. Yeah, so we use Minnesota NLP models, which are more latent and have high exact match accuracy. But we found that the most viable option for our pipeline is Minimum Uncase, which has a exact match accuracy of 78% and a runtime of around 305 milliseconds. Yeah, so we can see that Minimum offers the best performance to latency ratio. It was also pre-trained on Squad 2.0, so it has been already taken the unanswerability task, so it is better suited for production. Yeah. So while training on fine-tuning on the dataset, we observed that the accuracy fell from 78 to 74%. But while splitting it theme-wise in a ratio of 80-20, we found that the fine-tuning accuracy increases from 74 to 75%, but is still lesser than 78%. Yeah. We tried two kinds of data augmentations, but this didn't improve our results so much. This can be attributed to the fact that we took a much more lighter model and it's not as much latent as many of the SOTA NLP models. Yeah, we designed three kinds of decoding algorithms in order to best choose the start and end logit pair for the extractive span. We developed a novel algorithm of time complexity O of n log n by using binary search and kind of sliding window to reduce the search space and get a better time approval solution. Yeah, this is a unique and special part of the pipeline where normally readers use a threshold of 0.5 to predict answerability. But here we are using the ranker scores as well as the reader scores to predict answerability. This is based on the intuition or hypothesis that the most probable answers confidence score and as well as the ranker scores must comply with each other. And we saw a bump in accuracy from 95 to 97%. Yeah.
For rankers? So the final data that we're using for the pipeline, we are using knowledge distribution. So there are many elements we already pre-trained our marketing. So initially we have an augmented data set that is generated by where we have extra passages that are retrieved for each of the queries. So now on this augmented data set, they're actually no, the query is already given. The passage, the training data set that was given to us is used for augmenting the data set. So it is pretty much the exact same training data set that was given to us. So we are augmenting it by just for each of the queries we are just augmenting by mining hard negatives that are retrieved by big. So on this, we simultaneously predict the student and the teacher logics, and then we try to minimize the MSC logic. So this is for each team. Yeah. So what is teacher model for? So same thing. So it gives a score, a ranker score, which can be attributed as like if it has a higher ranker score, it means that there's a higher probability that the current passage has the answer. So it's like an ensemble of two models that you know. This is just a training method. So teacher model is also same as the student. Objective is same as student model. It has larger number of parameters, so it has more knowledge. The student model has less number of parameters, but the objective is same. So we want that we have less number of parameters, but the knowledge which teacher model has it also lasts that. Yeah, so the models it is not ensemble. Yeah, so this is a sort of a knowledge distillation setting where we try to learn from a better ranker, which is the teacher ranker. And we use a lighter. In terms of reduce, tweak the teacher model or student model? Student model is tweaked. Student model. And that's an explore game. teacher model. Yeah, it's true. It is just a way of fine tuning basically.
Because you don't have a clear answer, so you're using teacher answer.
Yeah, teacher logic score. So we tried like as I mentioned like cos so contrastive loss as well. It's a way of fine tuning, but we found that actually relying on a teacher model that actually produces a better ranking result.
So your assumption is that teacher model is good to predict.
Yeah. So if you see that it has an accuracy of over 90%. Because on fine tuning, the subset we had was very small. So fine tuning is quite focused on that.
But why didn't you use the teacher model itself?
Oh, it is very heavy. Right? So if you see the latency, it's around 3 times. It's around 1 second for each query. Whereas you see the fine-tuned model, which is the same as student model, right? It is 3 times faster. And almost has the same accuracy as teacher model. Because of this. Yeah. I mean, on a team dependent split. So, so we try for both combinations. Where we have two types of splits. Where one split has team independent, like teams are not overlapping, and one with teams overlapping, and both cases they improve.
When you were given that 30 team data sets, did you first figure out the finding model for each team or how did that?
Okay, so about team specific parameters, that uses the same method that we see, but it's trained on on specific teams instead of a split with
Yeah.
Yeah.
You were saying that you were able to achieve that much. I think that's the accuracy you are expecting.
Yeah, and the increment is about 2% in ranking accuracy. So the top one rank, how often is how does it do with just a universal vector which is trained on all the teams that are given, and this is team specific where teams of the same of a specific rank or a specific team is used for fine tuning. So this is just to highlight the adaptability for ranks.
And can you basically show the data optimization like
For rankers, for rankers, this one.
Data approval.
Okay. Okay. Two types of augmentations that we do. One for increasing the R negatives. We don't get into the details, but we mentioned this in the report. And other one is by changing the context of the surroundings. So we see how does the reader do. But we see that data augmentation doesn't help very much in case of readers.
And when a question comes something as you already answered the question, you are not.
We tried other methods for that, and we mentioned this in the report. Thank you.
Three, two, one, begin.
Good afternoon, everyone. We are team 43, and today we'll be outlining our approach to the DevRev problem statement. We were basically asked to create a system which, when given a user query, would search through a database of paragraphs and find the correct answer, and then it would return the correct context relevant to that question. This had to be done with three constraints in mind. The first was that we were only allowed to use the Google Colab free tile notebook without the use of any hardware accelerators like GPUs. The second was that we had to ensure that the model training time from start to end was less than 12 hours. And the third was that the average inference time per query should be maintained at less than 1 second. So let's start by going through our inference pipeline.
So we have divided our pipeline into 4 sections. That is, pre-processing and encoding, handling the frequently answered queries, selecting the context, and the question answering model. Firstly, we tokenize our domain-specific paragraphs, pass the paragraph sentences, and the already answered queries to our sentence into a model to get the embedding vectors. We store this in our database for a further use. As we receive a query, we pass it through our sentence encoder model to generate the query embedding vector. Now, moving on to the next question, using a query vector, we look for an already answered query which is at a minimum distance from it. To optimize this entire process, we make use of the already approximate nearest neighbor search using PICE library. If query is said to be found or matched if its distance from the given query vector is less than the distance threshold, which we chose to be at 0.2 units. If such a query is found, we retrieve its answer and paragraph ID from our database and present the answer along with the corresponding paragraph to the user. If such a query is not found, we move on to our next question. Next section. We identify the top 10 most relevant sentences based on the semantic similarity of the sentence vectors with the query vectors. We then combine these sentences to generate the context, and we filter the sentences as well on the basis of their relative distances. We also optimize the generated context by setting a word limit on the context. Experimentally, we found out that it performs best at 205 words. In the final section, we pass the generated context along with the query to our question answering model, which returns an answer if it exists. And based on the sentence of which the answer is part of, it also returns the corresponding paragraph ID to our user.
So now let's talk about the performance of our model. Firstly, we tried out a variety of different sentence encoders. MPNet was our best performer, as you can see from the graph. It provided us the most useful embeddings for our task. Google's universal sentence encoder is slightly less accurate than MPNet, but is 10 times faster. So we are starting to look into this. To further improve our MPNet model, we look into a concept called contrasted learning. In this, the idea is to basically reduce the distance between query vectors and the from sentences which have the answer, and maximize the distance between query vectors and sentences which are similar but do not have the answer. These triplets are isolated from our database training data set itself. For example, if we take an answerable query like this, the positive sample is a statement which does have the answer, and the negative sample is a statement which is similar but does not have the answer, and it confuse the model. This allows us to improve our F1 scores by 2 to 3%. Next, we look into question answering models. Here, Electra Best, a fine-tuned version of Electra Base, is our best performer. So, having a generalized QA model answer all the queries for all the different themes is not the most optimal way to do it. So, we deploy domain-specific question answering models. These are trained by fine-tuning the base model on clusters of interrelated themes. So 361 themes becomes 41 clusters, and then we train the base model on these clusters to create our domain-specific models. Also, for themes which have insufficient data available, we use synthetic data generation to create question answer pairs. This is accomplished with an ensemble of T5 small and SynQA. If species named entity recognition is able to isolate some named entities from the passage, it is passed on to T5 small, which generates question answer pairs. If not, it is given to keyword, which selects suitable answer phrases and then gives it over to SymQ to generate the questions. As you can see, we are able to improve the F1 score across clusters by 3 to 4 points. Lastly, to reduce the latency and model size, we look into ONNX graph optimization and model quantization. Using a standard format and also by reducing the precision of data types from 32-bit floats to 8-bit ints, we are able to significantly reduce the inference time. As you can see, quantized models are 1.5 times faster than unquantized ones, and they are also significantly smaller in terms of model size. Finally, we come to evaluations. MPNet and Electra Best, when fine-tuned, are our best performing models. They have a paragraph accuracy of 91% and an F1 score of 89 points. On average, MPNet takes roughly 60 milliseconds to perform the relevant context search, and then Electra takes 750 milliseconds to find the answer to the question. Interestingly, if we look at Google's universal sentence encoder paired with MiniLM, it is able to achieve a lightweight version of this pipeline, doing everything in 150 milliseconds. Now let's talk about the future scope and what we could do to improve our model. Firstly, we look into this approach where we use the MiniLM model in conjunction with Electra. We have a classifier decide which queries need the attention of the Electra model, which is more computationally intensive but provides better accuracy. And easier queries can be given to MiniLM, which is able to do this fast. Next, we look into mixture of experts. Here we have a bunch of different experts instead of cluster-specific domain, cluster-specific domain specific models. The question is passed to the experts, and then a gating network decides which expert is best suited for answers. Switch transformers is one way of accomplishing this basically. In this, instead of having multiple experts, we use one very large model and then have a router that decides what part of this model needs to be activated. The advantage here is that the computation becomes lesser for us, which makes this more efficient. That concludes our presentation. We would like to thank you for giving us the opportunity to work on this problem statement. We would now like to
Let's go back. You were mentioning that you are doing training for each cluster separately, right? What was the training time for each cluster?
For each cluster, it took almost 3 to 4 hours for fine-tuning on few folks.
And the accuracy metric that you were mentioning is for 3 to 4 hours.
This is for 3 folks, and a learning rate of approximately 1 by 20 of the learning rate that was used for pre-training, for training.
Let's go back to the contrasted learning. How do you what is of your pattern?
MPNet is fine-tuned based on this.
So essentially this is MPNet thing. Are you using a global encoder model for all the things?
So the thing
MPNet is basically a global.
So for all the things we have a single model, but that is being fine-tuned on the given data set, put into another. Sentence context is something you're doing.
Context switch. So instead of retrieving paragraphs, we are resorting to retrieve top 10 sentences that may contain the answer. So they are semantically more similar to the query. So based on those sentences, we give it to the question answering model, which based on that context uh, answers the query if possible. And given the answer, we just see where that answer lies, in which sentence it lies, and based on which sentence, which paragraph that sentence is part of, return the idea of that paragraph.
So basically, this reduces the latency since we are only handling 10 sentences at a time rather than 10 paragraphs and then finding answers.
So instead of giving a large document, we are just giving 10 sentences.
So in the question answering model there, you're using MXNet plus something.
Basically, question answering model is Electra.
Our sentence encoder model is MPNet and our question answering model is Electra.
And how do you pronounce it in the while you are just
Pronouns are basically handled while making paragraphs into sentences.
How do you do that?
Okay, so the sentence encoder makes contextual elements. So pronouns
fall in their context. We don't look into the actual grammar pronoun. The model is smart enough to understand based on words nearby. This is a pronoun, this has an answer.
So a paragraph has just 10 sentences. Are you passing each sentence to this encoder model?
No, we tokenize them first and then
So entire thing is passed from into encoder model. Then we take search on it for the relevant sentences, and those relevant sentences are then taken into question answer.
that combined essentially it's just concatenation of all keywords.
Along with some thresholds, like limiting the size of the context.
So eventually you figure out which sentence answer it and you just pick the paragraph.
Yes, exactly.
My previous question was essentially, for example, a sentence has let's say a noun and the second sentence has a reference to it.
We experimented with the context selection. So we tried taking a sentence. Suppose a sentence is the nearest sentence to the query. Then, based on in the paragraph, we are taking one sentence before that sentence and after that sentence. So even if it contains only nouns, it will also contains the relevant noun that pronoun is part of. So we tried with that, but the results were not that great. And
Actually, it added additional noise to it. And coming to your question, exactly what you need, basically the sentence encoder captures the contents. So if there's a reference to a noun in the first sentence and then it's referenced using a pronoun in the second sentence, it is effectively captured in the embedding. Now, when you use a similarity search, it is based on the distance of the embedding vectors. So this thing is taken care of. If there is a pronoun, it is a part of the context, and similarity search takes care of. And later on, we retrieve the sentence from the embedding.
And you were only doing the semantic search, very clear.
We experimented with various approaches, but this was the best approach that gave the best results.
And the overall latency is around 7.
Yes. If we use MPNet and Electra models, it is around 750 milliseconds. But if we use Google Universal Sentence Encoder for sentence encoder and MiniLM for question answering model, then it is around 150 milliseconds, with a reduction of around 5 points in F1 score.
What about the how big the context can be?
The one which is passed into the question answer.
We have set a context and threshold of 205 words.
Only 200.
Yes. I mean, we played with various length, and 205 words were the most optimal.
If there is a, let's say, the data will get updated and some questions are really big, so you will truncate the context, or what will you do?
We are basically retrieving top 10 sentences, and
So let's
we
say
are
one of the sentences, you are top 10 sentences or top 10 answers?
top 10 sentences that may contain the answer. Like based on the given data, training data, we have put these thresholds, experimenting on those.
Threshold of context size.
Yes.
Basically, if there are multiple sentences, say if of more than 200 words, the one with the answer would be top rank. So we have also we have also
Since you already have a training model for fixed context.
These are parameters that can be changed anytime. They are not based on models.
Because it's like a transformer model.
Yes.
Shall we start?
3, 2, 1, begin.
So this is the solution for T41 for DevRev. So the general pipeline consists of a retrieval model that retrieves the best passage for from the given set of passages, and then it follows the retrieval model which extracts the answer from the given best candidate passage. So in our pipeline, the information retrieval is divided into two segments. The first one is the bioencoder, and this is followed by cross encoder. Whereas we use a question answering model for retrieving the answer for the given query. So coming to the architecture, essentially we have the bioencoder architecture, which takes in a query, takes in a passage and encodes in vector space, and essentially narrows down the search space to a mere 15 passages. Whereas, but this does this independently. So in order to exploit the relationship between the query and passage simultaneously, we have to make use of the cross encoder. So using the cross encoder, we get scores for each of the 15 passages. We rerank them and we use the top 10. So coming to the training and fine tuning, we evaluate the bioencoder in zero-shot setting. The reason being these models are already trained on 1 billion sentence pairs. And the thing to watch out here is the selection matrix. So we make use of the mean reciprocal length at that 15, as well as the hits at that 15, and of course the latency. So the thing which we saw here was that District Roberta was the model which was giving us best performance, and it was comparable to MPNet, but it was doing that at a relatively lower latency. And for the cross encoder here, this is where our negativity, this is where we use the negativity of the passages. So basically we sample the hard negatives possible from using the pi encoder. We have the 1, 2 passage, 4 false passages, and we use the localized contrast to estimation loss, where our goal is to maximize the score between the positive passage and the query, and simultaneously reduce the score between negative passage and query. So we use the hits at the 3, hits at the 1, and the
So we use two types of data set splits in order to evaluate our cross-encoder models. The first is basic theme stratification, in which the themes, all of them are present in both text and frame. So it helps us to understand how our model performs on already seen themes. And the second is a novel approach of semantic data set split, in which we use the average passage embeddings of a theme as the theme representation. Now these theme embeddings are clustered into 10 clusters using k-means, as can be seen after 2D projection using PCA compression. The red part in test is completely away from the green part in frame, which helps us to understand if our model performs well on completely unseen themes. Next slide. Here we have the PyEncoder results. As already mentioned, MPQNet and DistilRoberta are similar in performance, but MPQNet has 2 times the latency. Both of them give us 95.31% of hits at the rate 50. So we use DistilRoberta. Moving ahead, we have the performance of the top 3 cross-encoder models. Out of these, it is only possible to train a tiny BERT model within the time frame. It gets trained in 2 hours 12 minutes and has a 96.16% of top 3 hit rate. Moving ahead, this is the theme-wise versus global model comparison. The global model always outperforms the theme-wise model in all the 10 clusters that we have seen because of the lack of training data for theme-wise fine-tuning. Finally, we have the CPU runtime for the entire pipeline, which is 0.88 seconds only for the pipeline and 0.6 seconds for the processor by the pipeline. We now delve into the question answering module. For our query, we have the top k retrieved passages. Now for each passage, we'll extract the answer span and a confidence score associated with that. For this, we take the query, concatenate it with the passage, reciprocate it by a separated token, and a CLS token is prepared. Next slide. We feed this concatenate string into a BERT encoder. We use the output embeddings to get a start and end probability for each token, and we use the CLS tokens output embedding to get the confidence score. Now for each passage, we have an answer span and a confidence score. We choose the answer span with the highest score, unless the chosen passage's confidence score is lower than a certain threshold, in which case we conclude that the query doesn't have any answer in the given passages. Next slide. Here we would like to highlight that in order to improve the robustness of a QA model, we have identified 14 themes in the fine-tuning dataset which do not have any question-answer pair corresponding to them. And for such themes, we synthetically generate question-answer pairs using a T5-based model which has been fine-tuned on square dataset.
We try different BERT-based models and also look at the results from the state-of-the-art ensemble retrograde model. From this table, you can see that although DistilBERT has the lowest inference time of 0.383 seconds, we have used Electra for our analysis because of highest macroeconomic score on both DevSet and TestSet. This slide compares the Electra model architecture from that of the both. The Electra model is trained on the output of LLM, large language modeling objective. Both generator and estimator network work together to form a GAN, but the generator's main function is to output high quality valid sentences, and the estimator's main function is to detect the synthetic ones. And the assumption is that the model will then learn the correction of sentences, which in turn ensures the high quality generation of text. We then move on to theme-wise analysis of QA models. This is done to get the best and the worst performing themes for each of the 4 models. In Electra, we can see that the lowest score is greater than 0.5, which is not true for any of the 3 models. And in table 2, we can see that out of the 360 one distinct themes, 50% of the themes have an F1 score of 1, and 96% of themes have an F1 score greater than 0.8 for the Electra.
So we now discuss the trade-off between inference time and F1 score. So for question answering system, we have 2 desirable outcomes. We want a high F1 score as well as we want a low latency. So here the models are arranged in a decreasing order of latency. As we go down the model, the F1 score also decreases, but 2 models stand out. We have the tiny Roberta model and Electra small model to stand out. But the thing is, the Electra small model has a lower latency. Hence, we use the Electra small model in our final pipeline. We also compare between Electra base and Electra small. They have very similar results, but the latency of Electra small is much lower on CPU. That's why we stuck with Electra small. We now perform an analysis on a global model versus a theme-wise fine-tuned model. So here we classify the passages into 10 clusters. For each cluster, we have a parallel score, F1 score for the global model and for the theme-wise model. If you go down the table, the F1 score does not follow a particular trend. For some clusters, the F1 score is higher, whereas for some it is lower. So that's why we make a conclusion in the end. So we did some other optimizations such as we reduce the latency. So for quantization, we use the ONNX model. So what ONNX model helps is that we can decrease the latency, and we also use previously answered questions to increase the latency using already stored models. So to conclude, we use a global model, and we reduce the latency using the quantization and already asked questions. Thank you.
How are you using the already asked query?
Yeah, so we are taking the query and we are doing some sort of filtering based on the articles and this and that kind of words. We append the theme to the query as well and use this whole string as a key and we store the retrieved result in the dictionary.
So, for example, if you get a new question, you will think that you will just see that exactly intersect or not.
After the stopword removal and the theme contamination to the string. Because the same question can appear in different things as well as
And the same question can appear in this different tokens. So are you taking care of that or not?
as a tag. No, we're just looking at the stopword. Yeah, exactly.
And also in stopwords, we are looking at some particular stopwords, not all of the stopwords.
Okay. Can you go back to the QA model that you showed? I believe you said that that is going up all part of all the paragraphs with object that you got.
Yes, yeah, yes, we are doing.
Okay, what's the order latency again?
0.8.
That's for the entire.
But for the QA model, the latency that we get for the first one is 0.1 second. And we have included in the value. So if we look at this table, so the latency per question is mentioned in this row. So you can see for Electros one, we have 109.
One is for one packet and one. And we are using after when it's optimization, we were able to use 5 within the 1 second time. By using 5 also we got 0.8 for the entire 1 million second. For the entire pipeline is 0.7.
So there's a training that we're using, and then there's a training
So we have a printout data set. During inference, we just see like what are the models that are performing extremely well and what are the number of themes that are performing extremely well. So for example, if you check Tiny Robota, 309 themes have a F1 score greater than 0.8 and Electra Small has 334 themes greater than 0.8. So while the overall F1 score is similar, Electra Small performs better on more themes. Like on a particular themes, it performs very well. So this number is taken average over all passages for a particular.
So the final node that you release less as small,
Yeah.
And k
equals to 5. And k is equal to 5 was achievable because we quantize the model using ONNS model. Thank you.
Is it connected? Yeah, it is connected. Live stream is on.
Slides on navigation. Just take it to slides on navigation.
Ready?
Give us a go.
3, 2, 1, begin.
Good morning, good afternoon, judges. Today, we, the members of P53, would be presenting a solution for DevRev, experts on answer in a flash. So this will be agenda for today. First, we'll explain the block level implementation of a pipeline. Then we'll delve into the specific blocks and discuss what all analysis we performed on the same. So this is our overall pipeline. For a given purpose, we first use the context paragraphs and pre-compute the embeddings to save time during the inference. And for a given input question, we first compute the embeddings and compare with the previously computed embeddings of the context paragraphs and find the top K matching paragraph embeddings which are more relevant to the questions. Now, using the subset of context paragraphs that we have obtained for the question, we pass it on to the cross-encoder model to find the most relevant paragraph for a given question. Now, using this most relevant paragraph and the question, we pass it on to a QA model, which is based on the transformer architecture to get the results. So these are the specific modules that we have used for each of the blocks here. So just to highlight the benefits, our pipeline offers a high degree of modularity due to the use of a block level approach. Also, the specific modules that we have used have been trained or modified for use of large data, and thus our pipeline scales well. Also, by a near state of the art model, the benefits provided to our pipeline are immense.
Details here is the embedding integration technique for faster and effective passive retrieval. Basically integrates dense lexical embeddings and semantic embeddings to generate dense hybrid representation DHR, which are flexible and effective to para retrieval than the existing hybrid techniques. It uses relatation, gradient of state, and produces dense vectors which are robust to execution. The training process of delayed CLSP involves concatenation of lexical and semantic vector to find the relevant score between query and passage. Further, why did we use delay? Delay was used to reduce the search space by finding the relevant context paragraph. We carried out exhaustive experiments to compare delayed CLSP with dot product similarity metrics with other combinations of embeddings and search methods. And we found that there was a relative increase in both para and QA scores by using this. This illustration here shows the comparison of delayed CLSP its counterpart algorithms over this metrics on the validation set of MS market data. Delayed within set of the most relevant paragraphs for the question. We also decided to fine-tune delay. We split the given data set of 75K into 80 templates for training, validation, and test. We fine-tuned delay up to 40K optimization steps and found that the para-accuracy of the base model, which is 99.68%, is better than the accuracy of the best fine-tuned model. Hence, we decided to move on with delayed CLSP as a base model in our final pipelines. Now, coming on to the cross-encoder. The cross-encoder is a paragraph ranking module, which is a transformer-based model. It takes two sentences as the input and generates score between 0 to 1, which depends on the semantic similarity between two sentences. It comes in a pipeline right after delay. It generates a score between 0 to 1 for each paragraph retrieved for delay, and hence returns the most relevant context paragraph. It is built on the mini-LM architecture and is pre-trained for semantic similarity on the MS Marco dataset. So why did we choose a cross-encoder? The incorporation of the cross-encoder pipeline led to drastic increase in scores, around 8.5% in the QA score and 9.5% in the PARA score. Another distinctive feature of the cross-encoder is that it uses Siamese and triplet networks to update the model traits during fine-tuning and training. And we tried several base models of the cross-encoder and found out that the L4 version of the mini-LM gives the best optimal performance. Now, to further improve our scores, we fine-tuned the cross-encoder on the train split of the 75K data set which is provided to us and found out there was a 5% increase in the paragraph accuracy, and hence we chose to move on with the fine-tuned version of the cross-encoder model.
Now coming to our QA model, we select Electra Small, which is the smallest variant of the Electra family. Electra is a transform-based model which has the pre-training task of replace token detection instead of the mass language model used in models like BERT, Albert. The major advantage that this provides is that it has a much lower compute requirement while giving better results. As you can see, we compared Electra Small with various other models of similar speed and observed that it has the best results. We also further tried to improve the Electra-based model, Electra Small model, by fine-tuning it on the test range. We observed that the base model still performed better and decided to use it in our pipeline. Now coming to synthetic data generation, we first take the input context paragraphs and translate them to French, then we back translate them to English. This preserves the semantic structure of the paragraphs while changing the lexical structure, so make it brand new fresh paragraphs. We generate the fresh questions using the T5 PLM, and then at last we generate the answers using Electra Large. We use the synthetic data to fine-tune our base model, and we observe that the base model still gives better scores, and hence we should proceed with that. Now coming to theme-wise analysis, we compute the theme-wise reference scores using the base model, and we take the bottom 16 themes, and we observe that on after finding the base model, the bottom 16 themes, the accuracy increases by 2% in the bottom themes versus, but we get a 3% accuracy effect on the base. Now coming to caching, we try to use the already answered questions to improve the performance of our pipeline in terms of both accuracy and speed. So we save the DHRs of the previously answered question and compute the cosine similarity with the DHR of the input question. If the similarity score is above a certain threshold, then we directly assign the paragraph. Otherwise, we compute the full pass of the pipeline. We observe that our pipeline performs much better without caching than with caching. To summarize our final pipeline, we use delayed CLSP based model for the search method. We use the cross-encoder fine-tuned paragraph method, and we use the Electra small base model as a QA model. As you can see here, we report a score of 92.8% F1, Para score of 95.1%, a QA score of 91.5%, and a mean inference time of 767 milliseconds. This has been reported on a 10% test rate. Now to highlight some of the future opportunities, we could use data-oriented improvements in our caching process, such as hashing for large number of questions. We could also use knowledge graphs as an alternative to sequence-based modeling. We could also use rule-based algorithms for answer validation. Thank you.
Yeah, open to questions. Can you go to the retrieval? So when you say lexical vector, what would it produce as in a word sort of thing?
So essentially, that is true, sir. For a given text sentence, it would produce its leading counterpart by encoding it. And that would be performed by Engram. I think for this model, it uses Engram encoding to produce this.
You can understand vector. If you are doing some sort of work to generate the variable semantics, what are you using for lexical?
So basically, it produces sparse lexical vectors. So the main purpose of using this is it transforms it into dense form, and then it concatenates the both in a semantic space to produce the overall final vector.
So essentially, you are trying the syntactic and semantic query model.
Yes. Other methods generally use either of these to represent text, but the superiority of delayed lies in use of both of these vectors to generate a tense representation that is small in terms and requires less computation to be performed right in the pipeline.
Also, it is quite a jungle technique, so it can be applied in a correct.
And was the improvement you got just having the semantic vector and having so that would be it's seen by this visualization. You can see there are other techniques like BF25, DOC, T5, and the scores were much lower when we compared it to the delayed CLS, which is in the last one.
Also, sir, in during a meta-evaluation, we use vector-based methods such as ANOVA and TAGS, but for them, we were getting a performance of around 70% or so. But for here, we got, I think, around 80% performance.
Here, what we are doing for the search, what are you doing?
So right now we are using the dot similarity metric, similarity metric to compute.
For a vector, how we find the nearest vector? Using the dot product, and we compute the scores of all the paragraphs which are present, and we find that which is the top one of them. You do an order and regression.
So actually, we tried to use algorithms like FAS and ANOVA, but what happened was in our data we had very few paragraphs per theme, and that's why the time it was much more than the accuracy. So we decided to stick.
What time does it take for a vector QA to be created?
This is synthetic. Yes.
What's the time for the complete pass? We are like for the complete pass, it was around 10 seconds for every because we are using back-to-back translation, which is a quite hefty task. We are using money to do that.
What happens in the case where you translate to French and you get the same sentence?
So essentially, sir, this is based on
one research that we have found that when we have two languages or different different semantic similarity that is decided by a score that is computed, it is a metric. So by translating into French and back to English, essentially what remains is the innate semantic understanding which the model has, but the lexical or the overall format that is given to us that changes. So essentially, the content of the given context paragraphs is retained, but the structure is changed.
Also, sir, we are translating the paragraphs which are quite huge, so the probability of having the exact same paragraph back again after the two processes is quite.
Can you please show the fine-tuning model of we are doing a fine-tuning on theme-based? No, we are doing it on a global scale. We have demarcated the data to create test and validation splits, and we are doing fine-tuning on the trained data set and evaluating on the valid data set. The test split is maintained for global evaluation of the fine. We actually use para accuracy as a metric to determine how our model was performing. Essentially, what para accuracy means is if we are in how to fine-tune work here. So essentially, fine-tuning is performed by the innate model that is used to produce the DHRs. That is essentially fine-tuning. How do fine-tune Yes. We are fine-tuning all the three models, sir, but we found that fine-tuning works best on the cross-encoder model, whereas the previous slide. For this module, sir, for the cross encoder, we found fine-tuning it on the train split of the 75K data set that was provided. But this is fine. This is not a fine-tuning on a Yes. Yes, sir. We actually test the fine-tuning process on a global level when we evaluate the whole pipeline, and we try to analyze the fine-tuning performance on a theme level for a QA model.
We have made the split with training every teams in all.
Training cross encoder, on a theme level is not done because firstly there is a huge amount of data that is required to train it because it's a fairly large model. Second thing is that the compute requirements required to do that was huge. In terms of the time provided, but that could have been done. Yes, so again, this is not a key-based, but on a for the train space that use. What is the we also do it on the theme-wise also. Please, can you navigate to that side? So we have the best teams and the worst teams. The best teams were those which had an F1 score of 1, sir, and the worst teams were those which had an F1 score of less than 0.9. So these teams the number of them came out to be 16, sir. And on these 16 teams, we picked up the questions and the corresponding paragraphs from the train split, sir. Again, maintaining that each of the data sets are independent of each other, and then fine tune on them. So on an average, we reported an improved F1 score of 72%, but there was a detrimental effect on the performance that the model gave on the best team. So therefore, we did not proceed with this. And 100%, you were able to achieve F1 score of 100%. Yes, sir. These were the best teams which gave an F1 score of earlier 1.
Yes, sir. We only show like the average of the whole.
The best teams, again, just to reiterate, are those which give an F1 score of 1 when the model is not fine-tuned in its base form. How does the para-accuracy vary with different values of So the para-accuracy essentially for large scale increased, but sir, there was a detrimental effect on the inference time of a pipeline because passing more amount of input to the cross encoder as well as to the QA model would decrease its inference speed, sir. So therefore, we found that the best mix when compared on a global level, that is the whole pipeline, was when we use k equal to 3. Thank you, sir.
Can I give a comment?
Three, two, one, begin.
Hey everyone, welcome to our welcome to our presentation on open domain domain specific question answer. Right. So first, let's look at our pipeline. Right. So as soon as we get our query, we have three major steps in our pipeline. Right. So the first thing we do is we check if the query is present in the FAQ database. If it is, we directly move on to the output. Otherwise, we move on to a retrieval step, where what we do is we convert the paragraphs into the sentence or mini paragraph counterparts, which are then fed into the retrieval model, and then we take the top k outputs which are dynamically chosen, right? And then we then convert this into a single context and then feed this into the QA model. Now, if the QA model is able to find the answer, we then move on to we map it back to the paragraph the answer came out from, and then move it to the output, right? And now let's look at the retrieval section, right? So, what is the standard retriever model? Basically, first they use dense or sparse embeddings to select the top few paragraphs, and then they re-rank it using a cross encoder. Now, this has two major problems. First is high inference time, and the second is context loss. So let's look at the high inference time problem first, right? So if you look at the architecture of a bioencoder, you see that it's largely independent for both the sentences, right? Not the same for a cross encoder. You have to feed it every single time during inference. Hence, if you look at the results, we see that even though the cross encoder might slightly outperform, you see that the inference time is not compensatable, right? So we choose the bioencoder approach and we make it much better later on, right? So if you move ahead, let's look at the context loss problem. Right. So the problem is any passage embedding is much more diluted than any sentence embedding because of mean pooling. Right. So obviously it's a much better representation in general. We are also able to control inference time because a passage is unbounded. So if we feed it to a QA model, the inference time is not in our control. However, we can control the number of sentences we feed to the QA model by dynamically selecting them. So we standardize the inference time while maximizing performance. Right. And also we're able to provide more informative context to a QA model. Right. Now let's look at our training methodology. So we define a new task called answerability. Basically, if a query and a context can answer if a context can answer a query, then we try to minimize the distance between the embeddings. So we use a Siamese network based architecture. Right. So what we do is we fix a teacher model and then we have a student model. And the student model learns to mimic the teacher model's embeddings when given a query context pair by minimizing the MSE loss, right? So you can see the results here. And if we move on to our fine-tune methodology, we see that we fine-tune using the MNR loss, which fixes an inherent problem in our dataset, which is in the fine-tune side, it's the absence of negatives, right? So it generates in-batch negatives and hence fixes the problem, right? And if we look at our right? So we fine tune at three levels of specificity: global, cluster on theme names, and local. Right. So basically, you can see that local or theme wise. So you see that at some themes we even get about 8 to 9% improvement. Right. So that fine tuning is pretty important. However, we can choose it depending on what kind of data and instance time we have, resources we have, right? Moving on. So what kind of runtime improvements do we provide? One, we cache the embeddings, hence we are able to save a lot of time doing inference. Second, we dynamically select the number of sentences to pass to the QA model, hence we standardize the runtime while maximizing the performance.
Now for the question answering part, for a QA model, the standard input is the context along with the query, and the answer is the extracted answer from the context. Now moving on to the training methodology. In order to make a model more robust, we tried model distillation. The teacher model selected was pre-trained on a dataset other than Squad 2.0, and the student model selected was pre-trained on Squad 2. However, as the training data provided was a subset of the Squad 2 trained dataset, the model started to overfit, and therefore we couldn't include it in our final implementation. Now moving on to a fine-tuning method, similar to the retrieval task, we have 3 levels of specificities, global, local, and cluster. The following scores are on the Squad 2 validation data. We can see that for both cluster and local, the F1 scores have improved a little bit. However, in the training test data available, more than 99% of the test data was part of the training data. So therefore, also training the QA model during our testing on generated data, the F1 scores dropped. Therefore, we couldn't include it in our final pipeline. Now for the runtime improvements, due to the highly optimized retrieval pipeline, we were able to use state-of-the-art Diverta VC base. In our approach, we have used point-and-X representation of the model. We can see that for the optimized and the quantized, the inference times are the lowest. However, due to incomplete quantization of Diverta, which is not supported currently, we finalized on using the optimized model of Diverta. There were some other approaches which we had tried but couldn't include due to certain constraints. First is Rust implementation of transformer models. During our testing on local runtime, we got a 2x improvement in inference times using Rust. However, it requires heavy compilations in a Python-based environment like Google Colab. Therefore, we couldn't include. Second is model pruning, which is basically sparsification of the model. It requires a lot of training time from scratch, therefore it wasn't feasible.
FAQ. So instead of using the normal standard approach of embedding similarity, we use a database of FAQ in which we paraphrase the questions that were already given. And then we used fuzzy match ratio to find out the similarity between incoming query and the questions in the database. Now, question generation. For question generation, we use the already existing answer-aware question generation pipeline, which first extract the entities and then generate question based on that. We further reduce the runtime and the high RAM usage by first quantizing the T5 and then using NER re-ranking algorithm. We also use domain adaptation like GPL and QC for QA, but both were time intensive, and that's why we could not include it in our final pipeline. Thank you.
Now we are open to questions.
Yes. Like one clarification is just that all our testing is on the validation. So it's the true test set which the model has not seen. Because most of the models are trained on the train set which was provided to us, already pre-trained. There's no point in testing on that.
You mentioned here?
Yeah, move to the pipeline actually. Move to the pipeline. Yeah.
How do you checking FAQs?
Right. So the problem with checking embedding this, let's say mother or father, so the embedding might be close. So we didn't do that. We use the fuzzy match code, say longest common substring sort of. So we generate the paraphrases to get all the different sorts of ways you can write that question, and then we do string matching, which saves time and more accurate, because the point is not to increase recall but to increase precision. Right. Fuzzy matching. Fuzzy matching. We included that at the end.
And how does it make paraphrases for the paragraph?
So essentially, the standard embedding approaches are lower precision approaches, right? And already our the pipeline that we had was under the 1 second mark. So we wanted to keep it safe and have a higher precision approach. Because we knew our pipeline gives the results, so we did not want to get a false positive in the ethical study. That's why we went with string matching based approach instead of an embedding matching approach.
But you are using an approach that says that if this or initiate check everything is for now. You're doing a paragraph embedding, you're going through the paragraph.
No. We convert the paragraphs into sentences.
You're going through the sentences, generating the embedding for that, and then figuring out the answer from it. So you could have done the same with the FAQ.
Right. See, like the problem with that is two sentences that might actually not have the same answer might be close in terms of embedding, and that's a false positive.
That's a false
Yes.
but that same.
But the QA model handles it differently, right?
So what you would happen is you might have just picked the let's say that person would have tried to let's say pick that paragraph and just use that paragraph to see if that can be answered.
Right. The problem with that is the paragraph length can be unbounded, and we wanted to standardize runtime. And our approach, we fixed the total amount.
You could have just taken sentence from that paragraph, which you now know that has the answer, and now you have the sentence, and now you can just do whatever you do in the last bit. Paragraph, two sentences. Again, does it take care of the references or it does not?
References that,
for example, the first paragraph, the second sentence has a pronoun that refers to.
right. So that is basically a hyperparameter of how many sentences you are taking, right? So that can easily be tuned on the data set that you have. Like we tuned it on our data set, we found that one sentence is the best because quad is a relatively simpler data set. But on larger data set, we can take more context in that will make this problem go.
Like since the key is dynamic, so we can choose a fine tune it according to the data set which is being presented to us.
You would say that you identify top K, what's the K that you.
Right. So basically, let's say we've taken the top 15, 20, and then we look at the number of tokens. And the QA model, we've plotted the number of tokens versus time, and we only keep putting sentences until the token threshold is within control. Yes, out of the given sentences.
Did it work well for you?
Yes, very well. They've clearly like over 15% advantage on the validation side, and with much better runtimes. Because I tell you, the Berta is the best model on spot validation within 1 second inference time. Right. So we were able to even incorporate that into our approach.
For retrieval was so far that you can directly use the state of the art model directly.
During semantic search, and how we are doing the identification of the topic.
Right.
The value of the key.
Yeah. No. So okay, that is just bind code or cosine similarity.
You got a vector.
Yes, we got the vectors. Then we do cosine similarity with the query of all the sentences.
Of all the sentences.
And then we select the top few.
Okay. Is there itself a time taking?
No, cosine similarity is a very fast process, and the embeddings can be stored.
For example, if you have let's say 1,000 sentences in a team, you are doing 1,000 servers.
So, like for example, if I give you raw numbers, cosine similarity can be done after like 10 milliseconds, 15 milliseconds. So it's not really a big constraint. The models have to make it.
Paragraph embedding the cache, like the sentence embedding cache.
I'm just trying to
Yeah.
make it time complexity.
Right.
So order and use the time complexity.
Right. Yeah. But that's only at the time of giving the paragraphs, the knowledge base, which is before the question. Right.
You got the question, so you are still doing an order and cosine similarity test, right? Or you are using some other algorithm to figure out the nearest sentence.
No, order.
Order. And can you just quickly tell about the fine-tuning improvements you have in both the paragraph and
Right. So we use something known as the MNR loss on the sentence. So, right. So it generates in batch negatives that helps solve it, and we see the results on the next page. Right. So you can see the results. And these are all on the validation set, which is a much different set than what we provided and give the two results. Right. See that even the top one sentence has 72%, which is much better. Which is much better than what maybe other methods that are talking.
And you get
Training. Fine. Question answering or
global sales point and local sales point 6.
That's only on top. Top one sentence, top 5, and top 10.
But at least for the top one, it's
Yes. No, sir. This is vanilla. Vanilla is the original. Global is we didn't look at the themes.
Yeah.
For global is 0.72, for local is 0.69.
No, but these are not the representative scores, no?
So like once. So vanilla is the original model, And then we didn't look at anything, we just took all the data and we fine-tuned. That is global. And then local is stabilized. And then cluster wise.
I just wanted to say, if you're asking these are final retrieval scores, these are not.
These are only on the testing we did.
No. Finally, the passage that we retrieved, this is not the score.
I'm just asking, is it looking at these figures, is it wise to create a local as a theme model, a model for a theme, or we should go for a global?
Because we take the top 10, usually top 5 to 10 sentences, so we get an improvement there. Because sentences are smaller in LLT, so the pure model can handle more. So we move on to the higher side, and that's where we see that, like you can actually see the cluster and local are actually close. So it saves time for the company also because we have to implement lesser models and save space as well. Thank you so much.
Whose is this? Who does it belong to? Ready? 3, 2, 1, begin.
Hi, this is speech and team presentation for learning domain integrated features for question answer. So we'll cover this presentation in three parts. We will first discuss the open domain question answering, then we'll find out how we extract an answer from given passage, and finally we'll go into how we adapt our model to a particular domain. So let's get into it. So for a given query, we have a list of passages, and the task of a retrieval model is to find the best passage which finds the answer to a given query. Retrieval models can be broadly classified in two areas, lexical and semantic. Lexical approach is a bag of words approach. It doesn't really take into account the grammar or the order of the words. But it is really good in datasets which are high lexical similarity, like our spot datasets. And those are there is semantic retrievals. These use sentence word transformers which get semantically meaningful embeddings. So why don't we combine the two of them to get our retrieval model? So we get the scores from our lexical model and the semantic model, multiply them to get the best passage that answers our query. So as you can see, this is our best semantic model and the best lexical model. Creating an ensemble, we see the scores far outmatch each of them on their own, creating impressive scores for top 1 and top 5 accuracy, taking around 100 milliseconds per query. So moving on to extractive question answering. Extractive question answering is essentially figuring out answer spans given a context and a query. So this essentially boils down to picking a reader model, for which we consider three models over here: the bird-based, the electra-based, and the deberta-based model. So we picked the deberta-based model for the reading task. That's because it is architecturally superior and uses a better pre-training objective, which is detecting the replaced tokens rather than large language modeling, which the bird uses. So moving on to the domain adaptation, where we try to adapt our model to a specific domain. So here are the topics that we try to consider broadly. So there's adaptation, where we try to consider contrastive and adversarial adaptation techniques. We try to perform synthetic question generation, which we'll get into in a little bit, and there's pseudo-linking. So for synthetic question generation, we consider two models. The first one is QAGen T5, which essentially uses an encoder-decoder architecture for generating question-answer tuples for a given context. And there is a question value estimation model, which is essentially trying to filter out which questions are best for training a model, the QA model. So it is a critical analysis of the questions that we want to ask when we try to adapt a model to a specific domain. So there's essentially two things over here. The number of synthetic questions required when we try to adapt a model to a specific domain. Let's say what are the number, let's say the number of questions that you require in order to adapt a domain that's let's say having a large domain gap when compared to domains that are quite similar. And then there's effectiveness of synthetic and real questions, for which we have provided this table over here. These are the experiments that we've done on the SCORT dataset. So when training on 5K training subset pairs, we achieve an FN score of 50.07 on the dev set. And when training on 5K synthetic pairs generated on the dev set, we achieve an FN score of only 31.70, which is a huge difference, which points out that synthetic questions are not as effective when it comes to generating, training a model to adapt to a domain.
So to adapt a retrieval model to a particular domain, we come across generative pseudo-labeling or GPL. So as you can see in the illustration, for a given paragraph, we generate some queries. Then a cross-encoder model reranks the retrieved passages, creating a pseudo-labeled dataset, which we then use to train our model on. We also come across Labrador, which is the state-of-the-art in domain adaptation for a retrieval. As you can see, Labrador uses 4 loss functions, 2 contrasting loss functions, and 2 retrieval loss functions, creating rich embeddings for a model to learn and perform well. But when we perform these domain adaptation techniques to our base model, we don't really see much improvement in the score, appreciable scores. So we'll get into the reasons why. So the base model which we're using is the NPNet base model. This model has been trained on a large group of question answering datasets, amounting to some 215 million paragraph query pages. Compared to SCORT V2, that is 1400 times larger. So what we find is that adapting to a particular domain leads to catastrophic forgetting for a model, which is undesirable. Our model is robust on its own.
So moving on to domain adaptation for the regional model, we essentially consider 4 algorithms over here. The first one uses contrastive losses with generated question answer pairs. The other 2 are state-of-the-art approaches which only use pseudo labeling instead of generating question pairs. And the last one is essentially the same objective function as the first one, but that uses pseudo labeling rather than using synthetic generated data. And that performs just as good as the one that uses synthetic generated data. So here are a few empirical results from our experiments. These are performed on the bird-based model and the devoter-based model, where we see that when compared to the zero-shot model, the synthetic generated data model, for which we use target data from the target domain, the synthetic generated data on the target domain, and the source data, performs slightly worse, like 2% worse when compared to the zero-shot model, whereas the one that uses only the contrastive adapting losses rather than the synthetic generated data performs 2% better. So that's essentially a 4% gap over here. So our models perform better when we do not use synthetic data. So now distilling all of our knowledge into the final pipeline. Here's the final pipeline, wherein we use 2 retrieval models. The first one being a lexical model, the Beam-Fit model, and the other one being the MPNet-based model, which is a semantic retrieval model, for which we retrieve the top 1 passage and pass that to the domain-adapted deburter V3 model, and that performs the reading task. And this is the metric score that we obtained, that's 79.03. Which is quite impressive considering that we are performing reading alongside retrieval. So here are a few future directions that we'd like to explore. We'd like to explore QA generation algorithms as to why they do not perform and have some reasons for those. Like we only have hypotheses for now. Then we'd like to explore phrase retrieval approaches as well. And there's active learning for query efficient learning on synthetic generated data, as we could not generate too many questions for the number of passages that we were provided with. Yeah. Thank you. The both lexical and semantic. What is the product of those both?
So BM25 is the lexical model and the MPNet based model is the semantic model.
Does that make sense to you as in the product of those both?
So the lexical model ranks the passages in an order. It is like
or it does make sense to use both of those and multiply those scores because that would consider the weightages of both of those. If you get a 0.7 score for one and 0.5 score for the other, that would bring down the total score. And if you get a 0.7 score for one and 0.6 score for the other, based on the 5 score, what does it look like?
So it ranks the passages on the
So it's like TF-IDF or what are we
It's
using?
quite similar to TF-IDF in terms of how it grades. BM25, did you like empirically saw what score BM25 is giving? Yes. So like the scores are in the range of 0 to 1. Yeah. So
I mean, even it's not in the range of 0 to 1, just to have a comparison to the other models, we can at least scale the score down.
actually you can't really scale that. So BM25 has a problem where the score increases linearly with the number of questions it has in the paragraph. So the score can go as high as 18 to 25. So,
But it will still be relative to the passages, right?
it will be relative to the passages, right? But that brings another, for example, now you have to kind of scale all the paragraphs for the top one paragraph score. And yeah, so I'm not sure. I think we have tried ourselves the paragraph, the product approach.
But this when you say anti-net base plus BF25, this means that you're multiplying.
Yes, we get the results from both of them.
But overall, you are seeing the improvement.
Yes, we see the significant improvement.
Well, as in the multiplayer network, we are getting 8.4.
That's the top end.
Yeah. And if we are doing a BM25, we are giving 89.
Yes, a top one accuracy of 7.
And we're using top one everywhere because we don't have the latency. Then we have quite a quick latency constraint, so we just use the top one and pass it to the people.
So,
so you fix top 5 paragraphs using the BM25 and using the embedding feature approach, and then you multiply the score of that you get from both of them, and then you come to the final score. So now since you are only fetching the top 5 for each of them, let's say
Sorry, the multiplication part is fetching the top 5 just. It fetches for all the documents, and then we create the final list, the top one and the top.
So the generative labeling that is mentioned for JSON, that is time generated.
GTL.
Yeah.
Generated pseudo value. Yeah, that is time intensive, and it doesn't really appreciably increase our scores as well.
Why do you think that is?
So we present the base model we are using has already been trained on a huge corpus, so it is already quite robust to domain shifts.
So you are suggesting that it doesn't really matter fine tune
This model has been trained to less than 20 databases, which were all reading paragraphs even to 20. So this is already familiar with most of the things.
is there a breakup of the time, like how much time do you take for the retrieval part and how much time do you take for the
So the retrieval models for the lexical model would take around 20 milliseconds for fetching a paragraph. The semantic model would take around 100 milliseconds for encoding the query and for the retrieval part. The reader model takes around 700 milliseconds. Thank you so much.
T20 or
I think you can just wait once.
Ready? Three, two, one, begin.
Good afternoon, judges. We are team 21 and we are going to present a solution for DevRev. So basically, this task is divided into two parts, where in task 1, we have to select a best paragraph for a given query for a pool of paragraph, which we will call as passive retrieval. And the other task being extracting the exact answer from a paragraph, which we call as question answering. So coming to synthetic data generation, we'll be using two techniques. One is negative sampling, and for that we have basically tried to remove the sentence which contains the keywords from all the paragraphs which can be answerable in the training data set. So this is basically done to remove the skewness of our data set and make it more balanced, and then use it further in our fine-tuning methods. And the other is basically paraphrasing our queries using a bar paraphrase. Now, for training, we had few design choices. So, the first one being whether using a classical based information retriever or a neural or a deep learning based retriever. So, we have tried to use combination of both to get better results. We'll see it further. Next, being whether to use a theme-wise model or a global model. For that, we have tried using theme-based impedance to get optimal result. And coming to a major question, whether we are using fine tuning or zero shot. So basically, our ensemble model perform much better for a given constraint on a given data set. So we are going to use our zero shot model. Other than that, in case of fine tuning, it was going under through some forgetting, which was reducing our performance and not getting a major push. So coming to our proposed approach, basically we have tried using ensemble, which is nothing but a two-stage approach. So what we have did is we took some classical IRs and using their top K paragraphs, we tried combining it using a similarity-based ensemble. And after that, in the second stage, we get a final paragraph from our classical approach and combined it with a deep-based approach. Now, how do we do that? So basically, we selected few classical approaches which were working pretty well on our data set. These are DF, Elasticsearch, and LSI. So we took top 10 paragraphs from all these methods and gave them weights according to their similarity score, which is cosine similarity. So these weights were 0.2 for TF-IDF, 0.6 for Elasticsearch, and 0.2 for LSI, which were obtained from our practical experiments. After getting the top 5 paragraphs from these top 10, we further combined it with a deep learning based model, and we got a top 1 paragraph. So it works because from our experiments we found that TF-IDF, suppose on its own on a trained data set, was 75% accurate on giving top 1 paragraph. After using this kind of ensemble, we are getting an accuracy of about 84%, and which is only a top 1 accuracy, and top 3 was much better, it was close to 94%. And why we are trying to use that? Basically, we are trying to use the time constraint thing, and we are trying to use the we are trying to use the keyword similarity of the classical approaches and combine it with the semantic similarity. So we try to complement the error of both parts, and it can be seen as a multi-step pre-wrapper. So
now that we have the paragraph from the IR part, we are extracting the answer from the paragraph by using a question answering model. We tried out various question answering models and we chose the best of them. So all the models which we were tried are already pre-trained on squad data set. And we chose our model as squeezebot and we tried fine-tuning on it. But then we realized that fine-tuning was not giving better results, so we went for zero-shot learning. And to improve the inference time, we used the quantized model of squeezebot. And to answer the questions which are already there in our knowledge base, we directly took it using hashing. Now this is the table of the performance of various QA models. The second column, which is accuracy, that's the accuracy which
whether the question can be answered or not from the given paragraph. And this is the exact match, F1 score and the average time per query. This is the these results are from the one theme of the training data, which was Beyonce. And as you can see, Squeezebot is performing really well, and it has 98 F1 score and average time to query is 350 milliseconds. And these are some more models which we tried on the same. It's a continuation of the table. And this is on the entire training set. It shows Electrosmall and Squeezebot as they are performing well. And we saw that Squeezebot continues to perform well. And after applying 12 minutes, the average time to query is 200 milliseconds.
So for the optimization of our pipeline, we observed that not all parameters were contributing equally to the results that we were obtaining. So what we decided to do was, first of all, we moved our parameters from a 32-bit space to an 8-bit space, so that our computation time is reduced and we save upon inference time. Secondly, we tried to make our models sparse by making some of the weights 0. It potentially eliminates computation pass and saves us around 60% of the inference time if we had not done this quantization optimization.
And now we just briefly talk about Squeezebot. Squeezebot is inspired from computer vision ideas. So in the last layers, we have a fully connected position-wise layer, right, in a normal world. So it is replaced by a convolution operations. So that is improving the speed by 80 to 90% in the last layer. So that's the reason we chose Squeezebot, to improve the inference time. And the rest are some of the models which we tried out. And Electrosmall is a generator discriminator framework, but we'll skip through all of this. These are not as good as the Squeezebot model.
So, in conclusion, basically our pipeline takes a query and it checks with our knowledge base whether the question answer pair is already available. If it's available, we are directly going to use that result. If not, we are going to pass it to our passage retriever, which is an ensemble retrievers, and we'll get a top one paragraph from it. An important point to note here is that we are going to use top one paragraph, but our inference time is quite less, so we can further improve it to top three paragraphs also. But we have went with top one paragraph because in task one it was mentioned that we have to select the best paragraph, and then passing it to a QA model, we are getting our final results. So this was our presentation, and yeah, thank you very much.
Can you go back to the retrieval question? Rather, to be very first, like we were talking about what's the time taken by the parameter?
So paraphraser usually takes around 1 second or 1 or 2 seconds per query. So since we have this synthetic data generation was mainly focused for us because we had to do fine tuning. But since we this would have taken a quite significant time, but we have figured out that ensemble of ensemble, the two-stage ensemble thing, was providing better performance than the fine tuning part. So we, in the final thing that we submitted, we did actually some part paraphraser. This won't be counted in inference time because we are computing those beforehand.
So you are still whatever model you are using, you are not using the negative sampling.
No. Negative sampling's main use was to fine-tune the deep learning-based IR model. But then we found that if we are fine-tuning the deep learning-based model, then we are compromising on some other aspects. And we found that even if we fine-tune it, the results which we get by ensembling it with other methodologies, they were better. And we were running a risk of overfitting because our trained dataset was relatively smaller compared to the original dataset on which it was trained.
Can you go to the next one? So you're doing a TF ideas, you're also doing Elasticsearch.
And
what else?
latent semantic image.
Okay. And okay, so M2 we are using to get the embedded methods.
Yeah.
Okay. How did we decide on the weights? Empirically.
Empirically, yeah. We are using the experiment.
Like these were obtained empirically, but in practice, if you want to find the correct weights, we can just run
So basically, we did an ablation kind of thing where we just performed on individual models and looked at what accuracy they were giving, and then they decided weights based on that.
The final second layer where we are saying weight 0.1 to classical layer. So can do empirically.
Yeah.
So you didn't try as in figuring out the formula that we are doing, a product for those two.
No, there was no need to take product of those two because we are trying to, it is working as a re-ranker kind of stuff. So if we have a semantic result which is getting the intent of both the pairs, we just need classical models with a smaller weight to re-rank those results and bump up our results. So it will work much better if we do an additional method rather than some kind of multiplication.
And here you are figuring out the top one paragraph. Right?
Yeah, we are getting only the top one paragraph instead of any top
For example, from the classical diagram, I got a result with score 8.
Yeah.
And from a DBA element, I got something with 0.9.
Yeah.
So we are saying that we take the multiplication.
Yeah, we will first normalize the score and then get the 0.1 weight to this and 0. Because both are top 5 and from those top 5 we will get top.
So instead of using cross encoders, we are using this as a re-ranker.
It can be considered as re-ranker and it's like a pyramid approach because we are getting top 10, then top 5, then top 1 using step-by-step re-ranking because it was getting much better result than
And to the next slide, to begin, we are not having any sort of fine tuning.
Yeah. Yeah.
And we are doing to figure out if the application has already been answered before. We are using our hashing. Yeah. Just like a hardcore intersection. Yeah, just a hash map here. And the overall inference time is which hashing? So we are going to do like polynomial rolling string hashing. That would be about. And the question size, the question length is very small, so it won't be much. Yeah.
And overall inference time after doing all this and optimization is barely 0 milliseconds. So we are using top one just to satisfy the requirement of task 1. You can easily go to task 2 and we can easily move it to top k, which is k can be 3 or something.
And that will bump up it to 94%.
Like the passage interval accuracy, whether the passage is in that top 3, it will be around 94%, but we are just going for top 1, which is 84% on train data set and 80% on our test data set, which will already have.
And even after doing top 3, we will still satisfy the constraint of 1 second. I'm wondering this, why are you guys doing a hashing of that sort when it's supposed to check the already answered?
Because it was seen from the train data set, like the query, instead of getting the stop words, they were very similar for a particular theme. Like the same question was getting questioned. In the train set, it was not there.
So you figured this out from the test set? Yes, that we are asking the same question and then you figure out the problem. Yes.
Thank you. Thank you.
should I let my other teammates join, or is it fine if I present from one account? Since all of us, since there might be some confusion in speaking from multiple different accounts. Could you repeat that, sir? There's a bit of an echo.
मैंने इसको लैपटॉप से म्यूट कर दिया।
Ayok, should I leave the meeting then?